Okay, very good morning, everyone. Welcome to week 2 of HSMA and our very first session this week, where we're going to get down into the details and some of the more technical aspects of modelling and data science. Starting this morning, we're going to be talking a lot about conceptual modelling, and I'll explain more about what that is in a moment. And you're going to try a little bit of conceptual modelling. Aspects of conceptual modelling anyway this morning, and then in this afternoon session we're going to be taking our first tentative steps into the world of programming and talking about some of the principles of programming based on how I learned 39 years ago now, which makes me feel very old for understandable reasons. So let's kick off with this morning's session. And first of all, we're going to talk about what is operational research. This course covers both operational research and data science. So let's start with operational research, or OR, as it's commonly abbreviated. Let's talk about what it is. So let's think about an example in order to think about that. So let's imagine that you run an emergency department, and that emergency department is struggling with lengthy waiting times, okay? And you know that in your system, patients are arriving on average every 8 minutes. They then wait to be registered at reception, and that takes an average of 2 minutes once the receptionist is free. And you've currently got one receptionist. The patient then gets triaged by a nurse, and that takes on average 5 minutes once the nurse is free, and there's currently one nurse. And the patient is then treated in a cubicle, which takes an average of 30 minutes once a cubicle's free, and there are 3 cubicles. So very simplified version of an emergency department. You come in, you register at reception, you get triaged, you get treated, you go. Okay, so simplified system, but hopefully we'll demonstrate what we're talking about. So in your system, you've been given the option to try and sort out this problem with lengthy waiting times, and you can do one of three things. You can increase the number of receptionists by 1, you can increase the number of nurses by 1, or you can increase the number of cubicles by 1. So you can have 1 additional resource. So what I want you to do is to think about the answers to 2 questions. First, how long do you think an average patient spends in the ED now? Imagine you've been given a year's worth of data, and you look back over it and you calculate how long you think a patient is spending on average in this emergency department right now. And then the second question I want you to answer is, which decision are you going to make? Which resource are you going to add? Are you going to have another receptionist, another nurse, or another treatment cubicle? And hopefully Sammy has posted a link. She's built up a little Menti quiz. Is that right, Sammy? Is that in the chat now?
Yep, that should be in the chat now.
Fantastic. So if you follow the link to that, then if you put your answers on the Menti quiz, we'll see what you come up with. You have until the end of this song in order to come up with your answers. And in keeping with the fitting with this program, this song is all about good Python code practice. So here you go. You've got about 3 minutes. Off you go now.
You don't need any curly braces, just 4 spaces, just 4 spaces. Wildcard imports should be avoided in most cases, in most cases. Try to make sure there's no trailing white space. It's confusing, it's confusing. Trailing commas go behind list items. Get blamed Titans, get blamed Titans. And comments are important as long as they're maintained. When comments are misleading, it will drive people insane. Just try to be empathic, just try to be a friend. It's really not that hard, just adhere to Constants should be named all capital letters and live forever, live forever. And camel case is not for Python, never ever, never ever. And never use a bare exception, be specific. Be specific. No one likes the horizontal scroll bar. Keep it succinct. Keep it succinct. And comments are important as long as they're maintained. When comments are misleading, it will drive people insane. Just try to be empathic, just try to be a friend. It's really not that hard, just adhere to
Okay, so hopefully you've had a. Oh, sorry. Let's just go back to that one. So hopefully you've had a bit of a chance to answer those questions whilst also learning about Python code and good Python code practice by listening all those subliminal messages going in. So I'm going to ask Sammy, what are the results of this little quiz? What are people saying? How long do they think people are spending on average in the emergency department now?
So it seems to be somewhere in the region of anywhere from about 30 minutes. I think we've got the top is about 480 minutes,
Okay.
and sort of a smattering of answers in between the two.
Okay, so 30 to 480. Okay, so a bit of a range there. We'll perhaps take a look at that in a moment. And what are people saying? Which resource do they think we should increase?
So Cubicle is the overwhelming winner. We've got 85 votes for Cubicle, 86, 27 for nurse, and none for receptionist.
Oh right. Oh, the receptionist is not going to be happy. They really wanted an extra receptionist, but okay. So looks like most people saying cubicle, but there are quite a few people saying nurse. So it seems to be about 75%, 25% split-ish. Okay, interesting. So that's generally what people say. So we'll come back to that. Oops. Okay. So we could have built a model to answer this question, and this really gets to the heart of what operational research is. And in building a model to answer that kind of question, there are some important concepts that we need to consider. So the first concept I'm going to introduce you to is something called a base case scenario. And a base case scenario is basically just a model, a computer model or a mathematical model of the system as it is now. Okay, so it reflects what is happening right now in our system. And the reason we create a base case scenario in our models is so that we can see how the system is currently working. We can try and validate the model we've built to see is it accurately or sufficiently accurately reflecting real life. But also it gives us a little bit of a glimpse into where the problems may be, where are the bottlenecks, where are the delays, by looking at that kind of system view. So that would help us in this example. That would help us answer the question how long we think a patient's spending in the ED now. But it also might give us a little bit of a hint about which resource we might want to increase, because hopefully we'll be able to see where the delays are building up. And that might give us a hint as to where the problem might be and what we might want to look at. But where we really the real power of modeling comes in is in something called what if analysis. And basically, what if analysis is the beautiful thing about modeling, where we take our model of the current system, our base case scenario, and we adjust and adapt that in some way, and play around with it and change the parameters to explore potential future scenarios. So how might things change if we were to add in a nurse or add in a receptionist, or we were to change this bit of the pathway so patients went straight from here to there and then went back to this, or we remove this bit entirely, or we add this bit in. Anything you can think of, you can adapt. And that's known as a what if analysis. You take your model of the current system and you play around with it in some way in your computer model, and you explore what might happen. And the real power of that is that you can then use that to try and predict what the impact might be if you were to make certain decisions. And that can therefore help inform the people who are going to be making those decisions by providing them with some sort of evidence base. Okay, so it's, and we'll come on to this later, it's very rarely about saying you must do this because we predict that the time will extend by, or the time will reduce by 12 minutes. It's very rarely about that. It's more about saying, we've tested out the different options. We think that the model is predicting that option A seems the better option because, and this is the evidence we're generating. So it's more evidence to supply to the person or people making that decision to give them some indication about what might happen. Okay, so in our example, that helps us answer the question, which resource are you going to increase? The model may not make that decision itself, but the decision maker needs to do that, but it provides some evidence. But it will also hopefully answer the question, well, what do we think the impact is going to be of that proposed change? Because we can then explore how long the patients are spending on average in the emergency department if we were to make change X. Okay. So I said we could have built a model to answer this question, and indeed we have. And in fact, you have been supplied with this model. Now, you won't be able to run it yet unless you've got SymPy installed. We will be installing SymPy next week as part of the virtual environment, so you'll be able to run this from next week. But for the moment, I'm going to show you the model. It's the file howlongspenddd.py. Now, first thing to say is don't worry too much about... let me just expand that a little bit. There we go, I'll zoom in a little bit. Don't worry too much about the details of this. I don't want you to look at this and think I'm very worried about understanding any of this. You're not going to understand this. Most of you won't understand this at this point. But I will tell you that in a month's time-ish, you will be writing models like this. In fact, you'll be writing more advanced models than this because this is a very simplified procedural model, and you're going to be writing proper object-oriented SymPy models right from the off. So, nonetheless, this will make sense. I promise to you. Once we get around to this, so don't worry about the details. Basically, what this is doing is it's creating exactly the system that I described, where we have patients who are coming in. They see a receptionist, then they see a nurse, a triage nurse, and then they see they get treated in a treatment cubicle. And you can see the parameters that we've got down here. We've got one receptionist. We've got one triage nurse, and we've got 3 treatment cubicles. So exactly how I described. I've set all of the times exactly as I said. I said they're coming in about every 8 minutes. It takes them about 2 minutes to be registered, about 5 minutes to be triaged, and about 30 minutes to be treated. I did use the word average. We are inputting distributions here. So not every patient will spend exactly 5 minutes with the nurse. Not every patient will take exactly 30 minutes to be treated. They will on average, the average patient, but there will be some variability around that. But these are the averages. So we're plugging in exactly the numbers I gave you. And what we're going to do is I said it, you imagine you're looking at it over the course of a year's worth of data. So I've run, or will be running this model for a year. The model runs in minutes, so I have to express that in minutes. And there are 525,600 minutes in a year. So that's what we're going to do. So let's now run this model. Let me close that. Hopefully you'll be able to see this okay. So let's run it and see what it says. So we're just going to run the base case scenario first of all, exactly what's happening now. Okay, so this has come out with some queuing times and average time in system. So we can see the queue for Receptionist, on average, is about half a minute, just over. The average queuing time for triage is about 8.5 minutes. The average queuing time for treatment is nearly 54,000 minutes. And that's overwhelmingly contributing to the average time in the system being just under 54,000 minutes. So you may have been slightly off, even those of you who went up to the heady heights of 480 minutes. Unfortunately, you're incorrect by quite an order of magnitude there. So a little bit off. Nonetheless, let's try again with your answers to the second question, or the first question rather, which is let's try increasing the various resources. Now, as I mentioned, by running the base case scenario and getting those results, it's probably given us a little bit of a hint about where the problem might be. And those of you that did, I mean, fortunately nobody said receptionist, and that's good. Those of you who said the nurse, you may want to rethink your answer. I'm not saying, we don't know what's going to happen, but I'm just saying there does appear to be a slightly larger queue just after the nurse than just for it. But nonetheless, let's try it. We'll go through the process. We'll add in, nobody said receptionist, but let's chuck in an extra receptionist and see what happens anyway, because it's quick and easy to do. And it would be if I could, if Zoom didn't place the bar exactly where I need it. So let's move that over there. Let's run that. See what happens. Okay, well, if you're bored of waiting half a minute on average with a receptionist, you basically wait almost no time at all now. So I guess that has advantages, but it's probably not going to be our biggest problem in the system. But none of you said that. About a quarter of you said we increase the nurse. So let's play out your version of reality. See what would happen in that instance. Again, I'll move this down here. And we can see, well, I mean, it has had an impact. Certainly, there was an average queuing time of about 8 minutes, although I'd say that's pretty good for an emergency department. I mean, that's gone down to almost nothing. So you can see the nurse very, very quickly in our new ED. So, I mean, that's good for patient experience. But you will also note that the average queuing time for treatment has then gone up. So probably not the best solution. Let's try the treatment cubicle. Let's add in another, which is what, to be fair, what most of you said. So let's add in 4 treatment cubicles. We did have 3 before. Let's see what happens there. Can we get down from about 54,000 minutes? Indeed we can. Okay, so now we're down to average time in system under 3 hours in this particular run of the simulation. I should say the results will be slightly different every time I run this. So if I run that again with the same numbers, it's slightly different again. And we'll come on to this in the discrete event simulation module, where these kind of models you typically run hundreds, sometimes even thousands of times, and then take results over those iterations, because they're stochastic models. They've got randomness in them. But nonetheless, we're getting a sense that we are way down from the 54,000 minute waiting time, 54,000 minute time in system that we had before, and we are now down to something that looks a lot more reasonable. So well done, first of all, to most of you who said that the treatment cubicle was the way to go, but you're all really rubbish at picking up how long they were spending in the system. Terrible, absolutely terrible. Okay, let's go back to the slides. So the whole point of this is to talk about what is operational research OR. And operational research is basically the kind of thing that I've just shown you there. It's applying modelling, simulation, and analysis techniques to try and help inform decisions and improve the quality of decision making. Okay, so it's doing this kind of thing. This is an example of a discrete event simulation, but there's other approaches that we'll talk about as well. So why might you want to do this kind of thing? What are the benefits of doing this kind of modelling? Well, first of all, there's the benefit of what we call emulation. So a model is basically a version of reality that we can play around with without risk or consequence. So if we were to try this out in the real world, what we probably don't want to do, particularly in a healthcare system or any other system where if we get things wrong, there could be a real risk to people, then we would rather play around with a safe version. So we can create a computer model where we can play around with things, and if it's an absolute disaster, then it doesn't matter because we haven't done anything in real life yet. We're just exploring in a virtual world. But of course, if we were to do this in the world and we get it wrong, then it might be really problematic. So that's a really key advantage of a modelling approach for these kind of applications. There's also a key advantage of speed. Typically, you can build, especially when you get used to doing these things, you can design and build these kind of models pretty quickly, and typically a lot more quickly than you can affect the real world changes. And particularly if you get it wrong and then have to reverse stuff, which adds on obviously even more time, let alone the risks and the problems that may cause. So actually building these things relatively, you can do that relatively rapidly, and you might gradually refine it, but you can knock up a model pretty quickly. There's also a real benefit in terms of communication. These kind of models can help people talk about the problem, because you can use that kind of shared language, that shared point of reference, by talking around the model and talking about the design of the model. People can talk about their system, and actually in a lot of cases, just talking about a system can identify potential problems, potential issues, and that in itself can sometimes solve problems. We've had many cases over the years where we've worked with people, and actually just by talking through the issue, talking through what's happening, they realise, oh, we didn't know that was kind of happening. We could probably do this, and we don't need to wait for the model. We'll make that little change, and that can make all the difference. And that kind of leads into this fourth benefit of systems thinking. It's very easy and understandable that people who are sort of deeply entrenched within a system very often don't have that kind of full system view about even sort of beyond their little bit of the system, because why should they? That's not their focus. But actually, by designing and building a model, it forces people to think about the system as a whole, and whether that's just thinking about the ED department or the larger hospital or whatever your system may be. Just getting people together that work in different parts of the system can be really beneficial and get them talking. And as I remember, many projects where just getting people in the room who hadn't really spoken to each other about this kind of problem and identifying things they didn't know were happening can be really beneficial. Sometimes you don't even need the model; it's just the process of going through and thinking about the system. And the fifth benefit, which is worth flagging up, is that of objectivity. So a model can be really useful in trying to provide some objective support for an argument. Now, I put on a big disclaimer here that that's assuming the model has been built objectively. You can build a model to say anything you like. So you need to be very careful about that. But assuming that you have been objective in your model design and the way you built your model, then it can provide that objective evidence, because everybody will be coming into a problem like this with particular views about what they think should happen, and a model can kind of provide the kind of objective evidence if it's been designed carefully. So that's operational research, and that's a big part of what we do. In fact, the Pencourt team, we were set up originally to do operational research. That's where the OR bit of our name comes from. We're an operational research team. But in more recent years, we've also expanded into data science as well. And data science, particularly applied data science, the kind of stuff that we are teaching on this course and that we do within our team, is similar in some ways to operational research, but also differs in many other ways as well. So data science is about using approaches from things like machine learning, statistics, data mining, and data analysis to try and generate some sort of insight from data that you have. So in operational research, we start with a system or a process that has a problem, and we use the data in order to say, well, we need to create a model of this system, and we're going to need data to plug into that model to try and recreate what's happening now, so we can then play around with that and see what might happen. But with data science, we start with the data. Okay, so the data isn't just something that we bring in to help us create our model. That's actually the focus of what we're trying to do. So we start with the data, and we use various techniques to try and look for hidden things that may not be obvious to us as human observers, to see if there are hidden patterns and structures in the data that might provide us with some insight, with some information. So OR, you kind of start with the system and process, and data science, you kind of start with the data. So it's slightly different kind of starting points, and therefore different approaches that you use. So to really hammer this home, an example OR question might be, look, we want to make these changes to our process for triaging patients. What do we predict the impact's going to be? What resources will we need to put in place to make sure this is as efficient as possible? So that's a kind of standard operational research question that you'd probably answer that kind of thing with a discrete event simulation, for example. Whereas a data science question might say, well, look, we've got lots of data on people getting readmitted. Can we teach a machine to automatically identify which patients are likely to be readmitted? So here we're starting with the process and the problem with that process. Here we're starting with the data. Okay, so that's the kind of key fundamental difference, really. So in the course, you will learn about lots and lots of different operational research and data science methods. Basically, most, if not all, of the things that are close to all of the things that we cover and use and apply or have applied within our research team. And these are some of the key things you'll be learning about over the next 6 months. Discrete event simulation, that's a big one that we'll be starting with after this module. Geographic modelling, again, another really key one that Sammy will be looking at after discrete event simulation. Machine learning, obviously huge now and a big part of what we do within our current research team. Natural language processing, agent-based simulation, system dynamics. These are the key kind of areas, and in particular, these top four, particularly discrete event, geographic, and natural language processing, tend to be the big popular ones for HSMA projects, understandably, because they approach questions of we've got a problem in our pathway, or we need to locate our services, or we've got lots of free text data and we need to do something with it. So, I mean, those are probably problems that you can all think of, problems like that in your organisations. So obviously a key part of the HSMA program is going to be you thinking about what project you're going to do and how you're going to apply these kind of skills, your new skills, to solve a real problem in your organisation. So I'm just going to give you a very quick sort of taster overview, 1 or 2 slides on each, just to give you a sense about what we mean by each of these things. And obviously we're going to cover all of these things in detail in the course. Many of them have their own modules. The module 2 is all about discrete event simulation, but this is just to give you a little bit of a taster, just to get you thinking about some of the problems that might be in your organizations that might fit some of these. So discrete event simulation is the thing you just saw when we looked at that ED example. So it's a way of modeling what we call queuing problems. Okay, so in a discrete event simulation, or DES as we commonly abbreviate it, you have entities that are flowing through and queuing up for discrete sequential processes that use resources. So to put that in slightly simpler language, imagine patients flowing through and queuing up for various activities that happen one after another within a patient pathway, and each of those activities requires a resource, whether that be stuff or staff. So might be a bed or a machine or a doctor or a combination of those things. Okay. So because of that, discrete event simulation typically used in health and social care to model processes and pathways. So exactly the kind of thing we just looked at, what happens when patients arrive at the emergency department, but you can replace that with anything like if you work at a GP surgery, how is the system working when patients arrive at the emergency department, the GP surgery. If you've got running a telephone system, how are telephone calls coming through, and how people are getting through to various bits of the telephone system. If you're running a blood test service, how are blood test results flowing through to the various stages, etc. So your entities don't have to be patients; they don't even have to be people. But where you've got things that are flowing through and different things are happening to them, and each of those things typically needs some sort of resource, that's a queuing problem, and that's a discrete event simulation problem, typically. And so the kind of what-if questions we ask for the DES are about some sort of change to a process or pathway, exactly as we just looked at. So typical kind of system here might be for a discrete event simulation, patient arrives, gets booked in at reception, just as we had before. That needs a receptionist. Patient gets triaged. That's an activity that requires a nurse. Then either nothing further may happen, or they might need to be seen by the doctor, and that requires a cubicle as well as the doctor. And then they might get discharged, or they might sadly die, or they might get admitted to hospital. And if they get admitted to hospital, they'll need a bed, and then they might be discharged, or they might die, and all those kind of things. So those are the kinds of problems that you'd look at with the discrete event simulation. To give you an example, this is a real project that I did a number of years ago, working with Royal Cornwall Hospital Trust, which was looking at muscle-invasive bladder cancer. So bladder cancer, certainly at the time, 7th most common cancer in the UK, and about a fifth to a quarter of them of cases had where the cancer had invaded the muscle wall of the bladder, which are basically the nastiest form of bladder cancer, about a 5-year survival rate of about 50%. And the definitive treatment is cystectomy plus chemotherapy. And they were basically looking to see whether they could speed up their processes, because basically you want to try and identify those with muscle-invasive bladder cancer as quickly as possible to get them quick treatment, and that can make a huge difference. It can mean the difference between life and death for these patients. So we built a model, a very, very simple model, I would add, very simple model of the system, which then we presented, and actually I went down to sit with them in a cafe, and we had a nice cake, and I showed them the model running live, and they all got talking about clinicians, the consultants there. We had the nurses, we had some of the admin people, and they just started firing ideas, and I was able to try them out live in the model and say, well, we think that will happen if you did this. And one of the key things they came up with was, do you know what, we're actually pretty good as consultants at identifying what we think are likely to be the muscle invasive cases. So if we were to fast track those patients before we have the test results back, what would be the impact? And basically the model made some significant predictions, basically that there would be about a 5-week reduction in referral to treatment time. That's huge when you're trying to identify patients who need to be picked up very quickly. And they put those changes in place pretty much as I was sat there. They started rewriting the protocol. I think it was on the Thursday, I think the Friday afternoon, and by Monday the new process was in place. And then they invited us back about 6 months later, and we looked at the data again to see what happened. And that's exactly what happened. They found that the mean time to being from referral to being contacted by the nurse specialist to discuss their diagnosis had reduced by 5 weeks for those patients who've been fast-tracked to the ones that they had identified as being likely muscle invasive. But wonderfully, it also reduced by nearly 2 weeks across all patients, even those that weren't fast-tracked. And at first we were like, why has that happened? Surely if you're shunting people to the front of the queue, even if they're supposed to be there, you would expect some sort of, a problem. And actually this is something that's quite common when you look at these kind of problems. It goes back to exactly what I was talking about earlier, just talking about this process, getting people, we had about 7 or 8 people in that group, just getting them all together in a room, identifying what was happening, what they could do, getting them thinking about the system. Just that process, leaving aside the model bit, was enough to start making them getting little improvements. They're just little things over here and there, and all of those general improvements had led to a general improvement for everyone. So the real power of the modelling process beyond the kind of technical model itself. Okay, so that's discrete event simulation, which I suspect many of you will go on to do in your projects. I would expect a lot of you are sat there already thinking of problems that you have in your organisations that kind of fit that kind of profile. Let's talk a little bit about agent-based simulation now. We've never had an agent-based simulation in HSMA. We had one last year. Unfortunately, that he had to pull out the program, but that was the first one we had, so we still never had. So I'm going to throw down the gauntlet to you today to see if any of you may come up with some ideas for some agent-based simulation. So my background is in agent-based simulation. That's what my PhD was in. And agent-based simulation are basically where we build a model that's focused not on the system, but on the way in which individuals within a system behave and how they interact with each other and what their motivations are. And it's focused on the emergent population level dynamics, the emergent behavior that comes out of all these little individuals interacting and doing their own thing. Okay, that's what an agent-based simulation is. It's commonly used in ecology. So if you, my PhD was in ecological modelling. It's really common there. They actually call it individual-based modelling more commonly. If you're an ecologist, if you talk to an ecologist and talk about IBM, that's what they'll understand. It's very common in that sector, and it's common because very often they know a lot about how an individual animal foraging might behave and what they'd be motivated by, they energy motivated, etc. But they may not know so much about what that means when you have a colony of animals that are behaving. What does that mean in terms of the landscape with which they're interacting, that kind of thing. And so it's very commonly used there. Basically, in an agent-based simulation, you have agents. They are moving and interacting within an environment of some kind, and that environment can be anything you like. And each of those agents has some form of individual level behavior. And the thing we're interested in is what happens when you put all of those individuals together behaving and interact. Okay, so I'm sure, based on last week's video, that Sammy will highly approve of this slide in particular. Yes, this is The Sims. In fact, this is the very first Sims. And yes, The Sims is an agent-based simulation. That's exactly what it is. Okay, Theme Hospital here a little later. No, sorry. That was before The Sims a little bit. Also an example of an agent-based simulation, probably more similar to some of the stuff that you may indeed want to do. And for those of us who are really old, you'll know that The Sims didn't come from nowhere. In fact, there was a precursor in the old days called Little Computer People, which was basically The Sims in the 80s, and was, again, a very, I would add, primitive, but nonetheless quite convincing for the time, agent-based simulation. You had little individual people, well, in fact, you only have one person most of the time in Little Computer People, but individuals who are have their own motivations, and that causes them to undertake certain behaviours and interact with each other. That's an agent-based simulation. So the next time you play The Sims, think, I'm playing an agent-based simulation. So example of that, as I said, for my PhD, I built a model called Harvest, for harvesting animals with reinforced values and estimates. I've never been good at abbreviations. Basically, the idea was, can we build a model of bumblebees foraging at large scales in landscapes? And the purpose was to identify, they thought there might be a risk if you bring in genetically modified crops into a landscape. We know that bumblebees travel large distances. They are significant pollinators that travel large distances. Is there a risk that they would pick up genetically modified pollen and then kind of contaminate non-genetically modified crops, which would obviously be a major problem. And the model actually predicted they wouldn't, for all sorts of reasons that you can read about. But basically the way we approached this was to build an agent-based simulation. And each of those bees had a goal, which was to fill up with food, i.e. nectar, as quickly as possible. And they made decisions about which field to go to based on where they thought was the best field at any time. Okay, and also use something called reinforcement learning, which we'll come back to, and we also cover in this course. Then we move on to system dynamics. So system dynamics, I will add in I'll be totally honest. I'm not a fan of system dynamics. We do teach on the course. I'm not particularly a fan. I think a lot of system dynamics models are not great. Having said that, we have had a successful system dynamics project a few years back. During the COVID pandemic, that one of the HSMAs had built and was really good. So you can get good stuff out of it, but it's often misused a little bit. But basically, system dynamics is a modelling approach where the thing we're interested in is kind of the way in which the system is set up. So discrete event simulation is all about the processes. You do this followed by this. Agent-based simulation is all about individuals who behave in certain ways and interact in certain ways. System dynamics is about how the system is configured and how that cause issues in itself, the way a system is itself is set up. Okay, so a fundamental principle in system dynamics is that structure determines behavior, and so we use causal loop diagrams to try and identify reinforcing loops, vicious circles or virtuous circles, depending on what the effect is, and also loops that balance things out. And they often use to try and model larger scale systems. You're sort of zooming out a little bit, or slightly more abstracted systems. So example here, very simple and slightly amusing example. This basically says that as the number of chickens increase, the number of eggs increases, and so that's a reinforcing loop. It's constantly snowballing, but as you get more chickens, you get more road crossings, which reduces the number of chickens. That balances itself out. Okay, a slightly more relevant example, perhaps, we have here. Imagine the number of people who are accessing GP services. As that goes up, the waiting time to see a GP goes up. As that goes up, the number of sick people in the community goes up, which means more people need to see GP services, which increases the waiting time, etc., etc. And also you can get a bit of spillover with, well, that also increases the number of people who may be accessing emergency departments, that kind of thing. So simplified example, but you get the gist. And that project I mentioned earlier from a previous HSMA, if you want to read more about that, really nice little project, there's a link here to a story about it, looking at capacity during the early stages of the COVID-19 pandemic. Geographic modelling, a big one for what we do. Geographic modelling is, if we split out those words, the geographic bit is asking where questions. So where should we place services? Where will patients go? Where do we find people with X, Y, and Z? And the modelling bit gives us the predictive power to answer those questions. So where to place services if our demand continued to grow, or if we were to close these services, where will patients go? Or if we find people, where will we find people with this disease, and how is it spreading? Okay, so that's the geographic and the modelling aspects of it. So previous examples, we've done lots of geographic modelling within the team, really nice examples that Mike and team have done around acute stroke services, looking to try and optimise where you locate those services, both within the southwest, where you've only got 14 possible locations, and across the country, where you've got 127 locations. And as Sammy will explain in the geographic modelling module, those are very different kinds of approaches. One of them is you can just try everything. The other you can't, and Sammy will explain more in that module. So I suspect you've all got location kind of problems that you can think about that would fit into that kind of geographic modelling aspect. And you even get these nice little maps that you can generate. That Sammy will show you how to generate this kind of stuff. This one's even compatible with a black and white television, which is an extra little benefit. Machine learning, I suspect you're all aware of machine learning. Indeed, it's often a motivation for many people coming onto the course. But basically, machine learning is where we're trying to get a machine to learn. And the thing we're trying to get it to learn is to make some predictions and gradually improve its predictions from data that we give it. And basically, the machine's looking for often hidden patterns in the data that can help it say come to conclusions like, well, if X, Y, and Z are like this, then I think the outcome will be this. Okay, so if I think I see this, this, and this, it's likely the patient has this condition, for example. Most of the machine learning that we will be covering in this course is what's called supervised learning. That's where it's type of machine learning that's most commonly used, where you have it gets feedback from examples. So we teach it and we show it the answers so it can try and improve itself. Okay. We've also got though unsupervised learning, which we don't really cover on this course, where we don't have it doesn't have the correct examples, often because we don't know what the correct examples are. That's usually where unsupervised learning is used. And instead, what the machine tries to do is to look for hidden structures to try and organize or cluster the data in a certain way to say these things look similar, but these things all look different to these things over here. So it's often used for that sort of automatic clustering of data. There's also reinforcement learning, which I mentioned earlier, that I used in my PhD as well, which is slightly different, which is where you've got agents who are interacting with an environment via trial and error, and each interaction provides some sort of signal to the agent which indicates whether the way in which they interacted is positive or negative, and if it's negative they get some sort of punishment, which is usually just the absence of being rewarded. And so what happens is the agents gradually learn to undertake things that give them reward. So we've got a session on reinforcement learning later in module 4. We don't go massively into it, but it is an interesting area. And again, you may well think of examples from your own organisations that might fit neatly into kind of a reinforcement learning kind of problem. I won't go into detail about this, but the Samuel project and its sequels are massive pieces of work for our research team led by our colleague Mike. If you want an overview video of the very first Samuel project, I'd highly recommend watching that. Really nice, easy intro to it. It's basically all about teaching a machine to try and predict whether a patient should receive clot-busting treatment if they've had a stroke. And there are various reasons why people can and can't have it. And it's motivated primarily by the fact that there's a lot of variation in terms of across the country, in terms of how the rates at which people are thrombolyzed, and it's most often due to the way in which clinicians differ in terms of their opinions. And so this tries to smooth that out. So really interesting project, and I'd highly recommend you have a look at that. Natural language processing, a big one. Where we're trying to use various techniques, often a lot of AI techniques that we'll be covering in this particular training, that attempt to deal with the interaction between us as human beings and computers via the mode of natural language. So that includes things like understanding how language is constructed, automating the extraction of information from free text natural language data, which obviously has a lot of potential benefits for health data in particular, and forming natural language in order to converse with a human. And that aspect of it we don't really do so much in this course because that's not what is going to be useful for you, but you will be aware of it. Things like ChatGPT that you are, I'm sure, aware of, have risen to prominence. ChatGPT being the chat interface that sits atop the GPT model. We'll talk more about how those kind of models work later in the course. But that kind of side of it we don't cover so much. But a lot of the principles that those approaches use we do cover because they are used in other aspects of natural language processing two. Some of the key things that that are potentially useful for your kind of applications and which we focus on, things like named entity recognition, where you can automatically identify things like people or places or names of things from free text data, and using various AI techniques to do that. That can be really useful. Sentiment analysis, which is where you try and use AI to predict whether a piece of text is positive or negative or sometimes even neutral in tone, so you can automatically work out and classify how people feel about various things, and you can often use these two things together to give you some really interesting information. And things like text summarization, where you can automatically summarize text into that sort of capture key information. And there have been some really nice previous HSMA projects that have looked at natural language processing. We had a project that used named entity recognition and some kind of text metadata, so stuff like the kind of language that a GP was using and how frequently notes were being added by the GP, by looking at GP patient notes to try and work out whether it might indicate an imminent hospital admission. Now, unfortunately, that project kind of fell over a little bit because of system issues, because they just bought a brand new system and that system was locked down and they had to pay a lot of money to get stuff out en masse, which is probably something that's familiar to all of you. They ended up having to try and do things manually, which it indicated some really interesting preliminary results, but yeah, a real nasty barrier, unfortunately, to getting that information out. We had a fantastic project a few years back. One of our policing associates who built this amazing tool that automatically identified the sentiment of every tweet to every police force in the country every day, and ultimately picked out all the things they were talking about, and that helped their social media team to be able to respond more proactively to things. In fact, they were so bowled over by what he'd done that they'd gone from saying you can't have any software installed. He had to do all this on his own laptop. Obviously, he was using what at the time was Twitter data that they used to make open and available freely, so it's public data. But they moved from saying you can't have anything to this is amazing, and they installed full Linux servers and Linux machines. This could be run within the police force. So it was an amazing sort of 180 on their approach to this, because they saw the benefit of this kind of stuff. Absolutely amazing tool. I'd encourage you checking out the video of that from HSMA 3. We've had a project that looked at using sentiment analysis to try and automatically classify patient surveys as being positive or negative, and named entity recognitions to try and extract the things that people were talking about in those kind of surveys. And last year we had a model that was some of the came along to the open day. I'm sure would have heard this presentation looking at trying to train a model to identify whether free text data that they picked up from social media sources between individuals, whether it contained mentions of illicit drug use, which were able to help them proactively identify particular individuals. So really interesting uses of natural language processing. Okay, I appreciate that was a lot of information to take in. You're not expected to remember all of this, remember all of the slides are available for your reference, but all of this stuff that we're going over this morning is kind of going to be fundamental for the way you design and conceive your kind of projects. So really important to think about that. We're going to take a short 10-minute break now. So normally, I apologise, we'd normally have a bit of an exercise now. We've changed this around a little bit. We've got a longer exercise at the end of this morning session. So we've got a little bit more to cover before we get to that exercise, but I'm going to insist you go and now stretch your legs for 10 minutes before we come back. So let's take a leaf out of a cat's book and go and stretch our legs. So see you at 25 to. Hi everyone, welcome back. So hopefully you've had a chance to stretch your legs now. First of all, my apologies. I'm just keeping my camera off for a moment. My cat has barged in during the middle of this. He is not waiting any longer for his treats, so I'm currently trying to multitask, feeding him treats whilst also teaching. Those of you who own cats will know the problem. So I'm going to try and multitask here whilst the see a cat on camera also has the same idea. They're not waiting. So first of all, apologies for any rustling that you might hear. Cat has typical cat sabotage. Yes, very true. So I will share my screen and do my best to try and teach whilst also feeding my cat treats. So let's see how well this works. Share my screen and let's go back to the appropriate slide here, which kind of says it all. Okay, fantastic. So let's move on to talk a little bit about conceptual modelling and problem structuring. So one thing that this is really, whenever you go through a kind of modelling project, this is the kind of cycle that you go through, and it's known as the modelling cycle. This is a cycle in which you start with some sort of problem, and via a process of analysis and conceptualization, you move from that real-world problem to what we call a conceptual model. We'll talk more about that in a moment. And then you kind of move from that design of the model to your actual formal model. My cat's now walking off, so I'm hopeful I've satisfied him at least for half an hour. So your formal model will be whatever your model is. Usually, in the case of HSMA, that will be your computer model. Apologies, give me 2 seconds. I'm just going to shut the door so I don't get interrupted again. And I'll just place my camera back. So most of the things that we teach you here are going to be computer models, although that could be a mathematical model, depending on what you're doing. Let me just re-enable things. Okay, I'm back. I'm catless. And then you would move from your formal model to generate some solutions from that model using your what-if analysis and the sort of things we talked about earlier. And then from those solutions, they would be passed to decision makers, and there would be hopefully some solutions that would be implemented to try and resolve this problem situation. Now, it's really important to point out this is not a linear process, and in fact, you'll often go back and forth amongst these stages a number of times. It's a very iterative process. So, working out how you're going to design your model from the real-world problem, which is what we're going to focus on this morning. That you'll be going back and forth with the stakeholders, the people who are involved in the real world system, multiple times to try and get that right. Similarly with this stage where you move from then how you're going to design the model to how the model is actually represented, again, iterative process, you'll constantly be getting feedback and going back and forth. Similarly, as you generate solutions from the model, some of those things will throw up extra questions that you'll then want to test, and you may even change bits of the design of your model and go right back here. So none of this is linear. There's going to be a lot of back and forth within any modelling project. But the thing we're really going to focus on this morning is this bit. So obviously a lot of the individual modules of the course deal with this bottom right bit where we move from a conceptual model to a formal model, how you're going to build a discrete event simulation, how you're going to build a agent-based simulation, how you'll build a machine learning model, all those kind of things. But this morning we're going to talk about this bit, which is actually really important and can be quite tricky to get your head around because of all sorts of assumptions about the way this should work that actually are often untrue. This phase where you go from real world problem to how you're going to translate that into a design for a model. Okay, and the conceptual model is really a kind of design, a blueprint for what your model is going to look like. So we're going to talk a lot about some of the things that you'll need to think about as part of that conceptual modeling process. One of the first things you'll need to consider, and probably the first thing actually, I would say that you should probably consider is why are you building the model? What is the objective of this model? What's the whole purpose? Why are you doing this? And it's sometimes quite useful to break that down and think about the different aspects of why you're building the model. And it's very useful to start with some sort of problem statement. So what is the problem? What are you trying to resolve? So it might be your problem statement is something like, there are significant delays in referral to treatment for our service. some sort of statement that identifies what the problem is that you're trying to solve, or at least trying to build a model that will provide evidence so somebody can try and solve it. You also need to think about what your what if questions might be. As we talked about earlier, the what if questions are the things you're going to explore in a model, the various scenarios to try and solve this, potentially solve this problem, or identify things that aren't going to work. So, things like, what if we reorganize the testing priority? What if we added in an extra nurse or an extra cubicle like we did this morning? What are the what if questions? And that will usually be in consultation with the decision makers about what might be possible. What could they potentially do to try and solve this problem? What do they want you to test in this model? You should also think about what the deliverables will be. What are the things that you're going to give to these stakeholders? So in some cases, it might be that you'll run the model, you'll build a model, you'll run the model, and then you'll give them a report which basically outlines the results of the model. But it may be more than that. It might be you give them the model, or you give out a model, and certainly the free and open source ethos of this program is that you would share the model. So you would make that available, even if the decision makers may not sort of adapt that themselves. But as Sammy will cover later in the course, when she talks about web development and developing web apps, a really nice deliverable that is often from an HSMA project is, well, give them a little app that they can play around with the model and try things out. And that's a really nice key deliverable for a lot of the stuff that you'll be doing, particularly the discrete event simulations, but also things like geographic modeling and all sorts that you can build the apps around. Excuse me. You should also think about what the potential impact is going to be, both for the organisation and its service users. So it might be well, if we were to solve this problem or reduce its impact, then what would the impact of that be? And it might be, well, potentially we could save lives, or we could improve the patient experience, or we could meet our targets, or a combination of those things. So think about what the impact might be if you were to achieve that. Particularly important as well for HSMA projects, thinking about what the impact is going to be of what you're going to try and do. Another thing you ought to consider alongside why you're doing this is what the scope of the model will be. And by scope, we mean what are the boundaries of the system that you need to model. So let's say, imagine that you're going to try and build a model of your emergency department. You might say, well, hang on, a lot of emergency department patients are arriving by ambulance, so should I build a model of the way in which ambulances are dispatched too? Well, it might be that you need to do that, but it's unlikely. You need to work out where you place the boundaries, because technically, any system that you model is part of a larger system. If you were to follow that through to its logical conclusion, you could conclude, well, I need to model my ED, which is part of X, which is also part of Y, and that in itself is part of Z, and you'll end up building a model of the known universe, which probably isn't going to help you. Okay, so you need to work out where you place the boundaries, and there are no right or wrong answers for a lot of this stuff. There's a really creative streak that you need whenever you build and design models, to think about how you're going to translate real world problem into a model. But there are some questions that that you can ask yourself that might help. Okay, so two questions in particular I always find quite useful when thinking through a design for a model are: A, what's the minimum that you can model to answer your question? And that can seem counterintuitive, because often, we'll come back to this, often people think, well, I need to stuff more in. The more I stuff in, the more detail I put in, the better my model will be. As we'll see later, actually, it's often the opposite is true. Often, the more detail you stuff in to your model, that means the more wrong you can be. And you just end up piling wrongness upon wrongness. And actually, very often, the simplest models are the most accurate and the most useful. That B model that I developed for my PhD was actually a pretty simple model, but actually turned out to be pretty accurate in terms of how it replicated real-world foraging. So don't make the mistake of thinking best models are those that are hyper-detailed. Very often, not always, but very often, the opposite is true. So think about what's the minimum you can model to answer your question. You're not trying to model every potential question in that system. You've got a specific question. If you've gone through the process of working out why you're doing this, you have a specific question or questions to solve a particular problem. So what is the minimum you need to model in order to answer your question? Because remember, it may be only part of the ED process that you're actually looking at. And in fact, that might mean that you only need to model a bit of your ED. It might be a really simple bit of your ED because you're not, the rest of it isn't going to affect what you're doing. Sorry, there's a really weird sound coming from my walls. I'm not quite sure what it is. We'll presume it's nothing important. If you do need to model other systems, a good question is to think about, well, if I do need to model them, how can I simplify them as much as possible? How can I simplify the representation? Because I don't really want to be going into having to model in detail another part of the system or another system that interacts, because that requires a whole new level of data. And again, more ways in which you can be wrong. So think about, for the purpose that I'm building this model, what's the simplest way that I can capture this? Also, another really good advantage of starting simple, you can always add bits in. It's easy to refine a model and add extra detail. It's much more difficult to take stuff out. Okay, start simple and see how effective that is, and then gradually build in stuff that you need, but only that which you need to answer the question. Sort of hand in hand with the idea of scope is the idea of level of detail. So scope is all about, where do you set your boundaries for the system you're modelling? Which chunk of the real world am I going to model? Level of detail is about thinking, well, how much detail am I going to pile into that chunk of the system, the real world system that I'm modelling? And again, there's no right or wrong answer. So you might have a very low level design for your model, something like, patient queues op, is it a Monday? If it is, then Julie will sign in the book using the red folder. But if not, well, if it's an odd numbered month, then if it's not an odd numbered month, Julie will still sign them in. But if not, it'll be John with the blue folder and then Derek. Now, that all may be really important. Probably isn't, but it depends what your question is. If you're building a model of the collation of the red and blue folders, then this is probably going to be exactly the kind of detail you need. But if all of this is irrelevant anyway, and for your particular question, you probably don't need that level of detail. Of course, you could zoom out to the other extreme and have a very high level model, and that model might just say something like, patient arrives, they get triaged, they get seen, and then they're either admitted or discharged. Now, that again is an extreme, but that might be all you need for your model. That might be exactly what you need to answer your question. Now, the reality is that most of your models will probably fall somewhere between those two extremes. But you should always be thinking about what level of detail do I need? And again, go back to those two fundamental questions. What's the minimum level of detail you can model to answer your question? Remember, more detail, more potential to be wrong. And if I need to model detail within other bits of the system or other systems, how can I simplify that? So always start from the point at which you are, ultimately you want the simplest possible model that is effective for answering your question. And to help you think about that, you should think about what the assumptions and simplifications are when you are designing your model. And assumptions and simplifications are similar but slightly different. So assumptions are things that we have to assume about our model because either we don't know how it works in the real world or we can't know. So example assumptions might be things like, well, we're going to assume that there are no travel times in the model within our clinic that we're modelling, for example, or that they're trivial. It doesn't matter, it's not going to affect us. Or we are going to assume, and this is a common one, we're assuming that the data that we've got, that we've plugged into our model, that is used as the basis for running our model, that is actually representative of what's happening. And that can be, and we'll come back to that later, that can be an assumption that can be problematic, and we'll look at ways in which we can explore that. And it's really important with assumptions and simplifications to you are going to have to make assumptions and simplifications. The important thing is that they are communicated clearly, so people are aware that this is how the model has been built. You've had to make assumptions and simplifications. All modelers do, but people are aware that those are the assumptions and simplifications that have been made. So simplifications are basically things from the real world system that we choose to simplify in some way because we don't think that the added detail, the added complexity is going to help us answer our question. It may even make things worse. It goes back to this point about, more detail could just mean we're going to get things more wrong. So it might be, common simplifications might be things like, the triage process, we're just going to simplify that down to patient spends an amount of time with triage nurse. That's the simplification of what happens in the real world. That the nurse will be doing all sorts of things within that, but it's likely, depending on your problem, that those little details aren't going to matter. It might be, it might be that your model is all about the triage process, and those are the little details that are going to help you answer your question. But if you're building a model of an ED, probably the triage process is just something you say, well, okay, patient's locked in with a nurse for X amount of time. That's how you would simplify. You might also look at the way in which patients can come into your system and say, well, we're going to simplify the routes that you can come into the system via ambulance and other, because actually anybody that doesn't come in by ambulance, the process is either the same or similar enough that it isn't going to impact our system. Okay, so it's all these kind of little micro decisions that you're having to make, but just being very clear about the assumptions and simplifications that you're making. So I keep mentioning this sort of more detail is more wrongness. Very famous quote within the modelling community from George E.P. Box, who was a British statistician, who had this famous quote: "All models are wrong, but some are useful." Okay. And it's actually, it's slightly amusing, and it's a nice little model. It's wheeled out amongst operational researchers. But it is actually really worth drumming that into your heads, that you are building things that are likely, that will be wrong in some way, but hopefully they will be useful. Okay. And they're wrong because they are simplifications of reality, but they're also useful because they're simplifications of reality. Okay, so their very disadvantage is also their advantage. And again, example, a lot of ecological models, not just the one I built, are often very, very accurate predictors, even though they're vast simplifications of what actually happens. They're not trying to model the intricate workings of a bumblebee's brain. Just by capturing simple rules of thumb, they're able to accurately predict what's going to happen. And so it's always worth bearing that in mind. And a little prompt down here. So I mentioned that in my PhD I looked at bumblebee foraging and modelled that. Very simple model, really. And I remember we did an empirical study to try and see how valid our model was. So I stood for about a week at Exeter University in a field behind the biology building, wheeling out in a wheelbarrow these oilseed rape plants, setting them up in 6 little patches that I then modelled in my computer model. And I sat there for 5 days with a dictaphone saying things like bee number 4 has arrived at patch number 3, it's now moved to a second flower. You can imagine I went slightly insane by the end of the week, but nonetheless, it was interesting. I then took those transcripts. The least fun part was then transcribing all of that, and then comparing what happened in the real world with what happened in the model. And it turned out the results predicted by the model were so close to the real world that when I showed it to my supervisor, he said, "You're going to have to check that again because nobody's going to believe that actually happened." But we did. We checked it, and it was true. So again, it just really emphasizes simple model can be really, really accurate predictor. So if you don't want to take the words of somebody who's considered one of the greatest statisticians of the 20th century, then perhaps you should take the word of a Cornish operational researcher who spent his life for a good week talking to bees and plants. Not drawing any comparisons there, Any comparisons you make are in your own head. Another example of this, here's the tube map, something you're probably all familiar with if you've been to London. The tube map is a model. It is a representation of the real world. That is a simplification. It is a simplification because that is what the actual layout of the underground looks like. And indeed, if you were presented with that, you would find it very, very difficult to work out where you have to go. Now, I would also argue, I remember the first time I used the tube, I also found this pretty difficult to work out where I was going to go, but that's probably more down to me. But it was certainly better than trying to understand that. Okay, so here's an example, model, vast simplification of what's actually happening in the real world, but really useful because of that simplification. Another example, perhaps more relevant for some of the things you might be doing. Here's an example of a model. This is a real model that our colleague Tom did many years ago, of a cardiac intensive care unit that has infinite capacity. Now that clearly is absolute nonsense. No facility has infinite capacity for beds. Okay, but so that's a model that is wrong. But it turns out that kind of infinite capacity model, and that's a thing in operational research, is actually really useful because it allows us to then assess the trade-off between having more beds and reducing bed blocking. So you can say, well, what's the point at which we get diminishing returns? Is it worth, for example, having 18 beds versus 17 when actually the difference is negligible? And probably actually we may only need something like 10 beds, for example, before we start to get diminishing returns. So those kind of infinite capacity models, clearly wrong, but useful. And typically models tend to come in kind of two flavors of simplification. You've got very simple models that will give you a kind of feel for the direction of travel, and then you've got very high fidelity models that are very detailed, that tell you exactly where you are and where you're going and what time you're going to get there. Now, the kind of models that you'll be building will almost always be this kind. Very simple models, or typically largely simple models, that will kind of give you a sense. And it's really important to understand, as either a creator or a user of a model, to be able to distinguish what kind of model this is that you are building or using, and to make sure that the people that are using it, if you've built it, are aware of what kind of model this is. So you don't give a model over that is this first kind, that predicts that if they were to add in a nurse, the average waiting time is reduced by about 12 minutes. And then when the average waiting time doesn't reduce by exactly 12 minutes, they come back to you and say, well, your model's wrong. It didn't reduce by 12 minutes. It reduced by 17 minutes. And they probably wouldn't complain if that happened, but if it went the other way, maybe. Very often people can think these things are crystal balls. They are not crystal balls, unless you're building this kind of model. But they are much rarer, and that's not the kind of thing you'll typically be building, particularly for the kind of problems you'll be looking at. So, important concept whenever you're designing your model, when you're building your conceptual model, your blueprint, is process mapping, trying to understand and capture the various processes within a system, and how things come into that system and how things leave that system, to try and understand how the system works. And that's a vital step in designing a model, because how can you possibly try and build a model that will hopefully improve a system if you don't know what the system looks like in the first place? Okay, you have to start from somewhere. You need to build your base case scenario, and that's part of the reason you do it. You need to understand how things are working right now. Otherwise, you've got no idea if you've made things better or not. So you need to start with some understanding about how the current system works. Particularly important if you're doing a discrete event simulation, but this applies to any kind of model. But particularly for discrete event simulation, process mapping, because it's dealing with sequential processes, is a really useful tool. So when we talk about a process, what do we mean by that? Well, processes are basically activities that have one-to-many steps and which transform inputs into outputs. So if we think about it in that sort of more generic way. So if we think about it in that kind of way, processes are a bit like functions. Okay, a function takes it may take 0 inputs, but it will take some form of input likely, and and it does something with that input or those inputs, and it spits out the other end an output or some outputs. Okay, and processes are the same. And a really key tip to remember whenever you're doing any process mapping, fundamental rule, we turn to our friend Roy Walker, who used to present Catchphrase in the old days. We all thought he was talking about the Catchphrase game show. No, it turns out Roy Walker was talking about process mapping, because he said, say what you see. And that's exactly what you need to do whenever you are process mapping. So some really good tips when you're process mapping: have very clear start and end points. Okay, goes back to a bit of the scope of the model that you're going to be building. That will help you define where you set your system boundaries. And it might be there are multiple ways in and multiple ways out, and that's okay as long as they're very clearly defined. How people can come into the system, how people can leave the system, etc. You should also, thanks Roy, you should describe what really happens, not what should happen. Say what you see. What is really happening? Not what's supposed to happen. What is happening in the real world system? Having said that, you also don't want to worry about little one-off exceptions to the process, unless they're particularly important. Maybe those one-off exceptions are the problem, and that's what you're trying to model, in which case they do become incredibly important. But usually, kind of things, well, we want to have this case where we did this and then this, it probably doesn't matter in most cases. So describe what really happens, yes, but what typically really happens. Really important whenever you're doing any process mapping, you need to map as a team. You need to get as many people in that room or on that Zoom call together as possible, who are involved in that system, ideally from different parts of the system, because each one of those people is going to have a different perception of how the system works, and everyone needs to contribute into that. You will be amazed at how many times you'll get people together who all work in the same system that all think it works in a slightly different way. And you'll be sometimes a completely different way. It's quite amazing to watch some of these process mapping sessions. So really vital you get multiple people, as many people as possible who are involved in the system, because as I said earlier, those kind of conversations can be valuable in themselves for trying to solve a problem, but you do want to make sure that you're getting as accurate a representation about what's really happening as possible. If you just have one person, you will just get their opinion on what the system looks like, which may be valid, it might be right, but it may not be. So you need to be very aware of that. You need to think about, whenever you're process mapping, so what is the journey of the entities, whatever the entities are that are flowing through, usually with patients, but not always. If you're building a telephone system, it might be, telephone calls going through, what happens to those telephone calls, what happens to the test results if you're building a test, a model of a testing process. Whatever your entities are, how do those entities flow through and flow between the various processes in the system? So you're following that journey. And then you're creating a visual representation of that journey, of that system, which is your process map. Now, it's really important to point out that you will likely end up with a really big process map. And the whole point of conceptual modelling is that not everything in your process map will need to be in your model. That's the whole point, okay? The process map is it's trying to catch everything that's in the real world system. As a modeler, you then need to decide, okay, so that's what's happening. What chunk of the system do I need to capture here? That's your scope. How much detail do I need to go into in order to answer the problem statement and the questions that you to answer the questions to solve your problem statement. So all of those things need to relate back. You need to think about what it is you're doing, why you're doing it. Therefore, how much of this big process map do you now need to capture, and in what level of detail? Okay, so don't make the mistake of thinking that you will translate a process map and then you have to code all the bits of the process map into your model. That will very rarely be the case. It might be for very simple systems, perhaps, but in most cases, half of that you won't put in the model. But it's really important that it's captured. And it might be, sometimes you even have to put in little bits into your model that as a modeler will make no difference, but it might help build credibility. And sometimes you have to do that in terms of working with your stakeholders. So you may end up with a process map that was like this. Is a real world process map that I did many, many years ago, back in 2014, looking at cardiology outpatient processes at Torbay Hospital. I seem to recall that this project never actually went anywhere in the end. They had all sorts of issues with the data, which is also another common problem you'll encounter. But certainly, if I built the model, I would not be building a discrete event simulation model that looked like this. There would be, depending on what, I can't even remember what the question was now, but I think it might have been identifying a bottleneck in part of it. You would think about what bit of that you need to carve off, and how much detail you need to represent, and therefore that will help you answer, okay, so what data am I going to need in order to build that bit of the model that bit of the system as a model in that level of detail. And you can visualize your process maps however you like. Again, there's no right way of doing this, but it is fairly common to use this kind of flow chart structure when you build a process map, because a flow chart allows you to capture flows and processes and decisions and all that kind of stuff that you commonly want in a kind of process map. So usually you end up with a process map that will look like things like this, where you've got entry points and exit points and rectangles for your processes and diamonds for your decisions that are made, that then little arrows point out to different processes. That's typically how you do it, but you can do it however you like and however suits your the stakeholders that you're engaging with. And I keep talking about stakeholders, and apologies for the dreadful pun in this image, it made me chuckle. But stakeholders are indeed individuals or groups or both who have some kind of interest in or an influence on or both the problem that you're trying to solve and or its solution. Okay, and it's really important that you think about who your stakeholders are for a particular problem. And the way in which you do that, again, there's no right answer, but there are some questions that can help you think about who the stakeholders might be. So you can think about, well, who owns this problem? Who might benefit from its solution? Similarly, who might suffer from its solution? Who has a legitimate interest in the problem and or its solution? And who has the power to influence the process of solving the problem and implementing the solution? Those 5 questions will help you identify people that are, or groups or both, who are potential stakeholders in this project. And this process is known as stakeholder analysis, and it's particularly important to identify who your stakeholders are. The reason for that is, well, there's multiple reasons really. First of all, you need to know who holds the information you need or the data you need. If you're building a model, you're going to need to get all this information from people. You need to get the right people in the room to build your process map. You need to know who those people are. You also need to, once you've worked out how you're going to design your model, that will help you work out what data you'll need. You need to know who to speak to, who's going to hold that. You may even need to go to a different organisation. All that kind of information, the kind of practical aspect. But you also need to think about some of the softer stuff as well. Building models, the whole purpose of the stuff you are being trained to do is to build models that will hopefully have a positive impact and make a real change for your organizations and for your service users. And an important part of that is building engagement. There is no point in you building the best model in the world that is super accurate and really impressive if nobody is actually engaged in it and nobody trusts it. And it never gets used. Completely pointless, just sits on a shelf. The whole point of this is to get stuff in use. And so you need to be thinking about how you build engagement, and actually stakeholder analysis is a really important way to do that, because you can identify who you need to engage with and how you will engage with people in different ways, depending on where they sit on the stakeholder spectrum. And you might need to know who's going to help or hinder you and how you might tackle that. And you might need to identify whether there are any potential conflicts that might impact what you're trying to do and how that might be mitigated. So a good approach for doing this is to build what's called an interest-influence diagram, which is a very simple diagram where you have interest on one axis and influence on the other. And you kind of carve it up into 4 quadrants, okay? So you've got stakeholders who are highly interested in your problem and its solution, and highly influential. At the other end of the spectrum, you've got people who aren't very interested and aren't very influential, and then you've got a mix of the two. You've got people who are very influential but aren't particularly interested, and you've got people who are really interested but can't actually do much. Okay, and the way in which you deal with those different sets of people will differ. So people who aren't interested and can't really do much anyway, even if they were, you probably just monitor them, because they might suddenly become very interested if certain things happen, or might become influential, or both. So you kind of monitor that group. The other end of the spectrum, those who are both highly invested in terms of their interest in it, and they're able to actually influence the success of the project. Those are the people who are your key players. Those are the people you probably want to be working with on your project team. They are the people you will be engaging with all the time. They are your key stakeholders. And then you kind of got these mix of people that sort of fall into one or other camp. So you've got people that aren't particularly interested but will be very influential. Might be very senior staff who can really change things quite rapidly. You want to keep those people satisfied, whereas people who are very interested but can't do much about it, well, keep them informed and make sure they're aware of what you're doing. Basically, all you do, stakeholder analysis, in identifying these stakeholders, plot them on an interest influence diagram, and you can kind of identify, it helps you just think about how you might deal with different groups of people, who you might involve as your kind of key stakeholders, etc. So it's just a way for you to kind of frame it in your own head. And it's, again, there's no right answer. You could not do this in this way, but you want some way to be able to think about who your stakeholders are. You're going to need to engage with stakeholders. Whatever your project is, you will need to speak to other people, and you'll need to involve other people. And that kind of leads us neatly on to a stakeholder that is often forgotten, but is in some ways the most important stakeholder of them all, and that is your end user. So whether that's your patient or service user or whoever it may be, depending on the kind of organisation you work for. And patient public involvement, PPI, is a really important aspect of any applied research project, not just modelling and data science, anything really where you are applying research to make real world changes. And PPI basically ensures that the voice of the people that are being affected or potentially would be being affected is heard. And PPI is often described as you undertaking research with or by service users, as opposed to you're doing it for them or about them. Okay, and that's the kind of difference with PPI, getting patients involved versus not. So good PPI should effectively be a really active partnership between the people doing the research, i.e. people like you who are going to be doing this, and the people for whom are going to be affected by the outcome of this. And it's really important to understand the difference between involvement and participation and engagement. It's kind of a spectrum that we see of increasing value. So at the lowest end, we've got the idea of participation, and where you've got patient participation is where you've got things like people taking part in a study. So they might be recruited to a clinical trial or asked to complete a survey. So they are participating in the research, but they're not really involved. Okay, they're just a participant in this general project. The next step up, which is a bit better, is where you've got engagement, which is where you're doing more than just getting them to sign up to something or fill in a survey. You're getting them actively engaged. So you are going to talk to them, presenting work to a patient group, or maybe advertising the study on various social media channels or whatever it may be. So you're making people aware of the thing you're doing and what you're doing, and keeping them updated. So that's better than participation. But the gold standard is involvement, and it's the hardest one to do, but it by far has the most amount of value. This is where your service users, your patients, whoever they may be, are actively involved in the project. They are part of your project team. They help you design what you're going to do. They agree what the priorities are with you. They feed into the decisions you make. They check the The design decisions, when you're building your conceptual model, they are part of the group that will help give you feedback about that kind of thing. They would even potentially co-author on publications that you write. So this is a really different level of engagement to just, getting somebody to complete a survey, or even, telling them about something. They are part of your project team. It is the hardest to do, but it is by far the most valuable. And this is really important stuff because, for a number of reasons, people who are affected by research, and in a lot of cases, the people who are sat here now listening, you are going to be doing stuff that is going to affect people. They have a right to have a say in it, fundamentally, to have a say. This is going to affect them, and they have a right to be able to understand why changes have been made, how you came to generate certain evidence. I remember this is very similar to the concept of free and open source that we talked about last week. That's exactly the same principle, that people have a right to be able to interrogate and to understand. But also, beyond that, the fact is that the actual quality of the research, the quality of the stuff that you're doing can be improved enormously by getting real service users involved. And they'll often contribute things that you won't even think of that are actually fundamentally important for the system that you're trying to model. And you won't even if you speak to all of the doctors involved and all the nurses and all the admin people, and I bet you none of them will come up with something that one of the patients says. So it's really important to get that voice in there as well. And it also ensures that everything that you do, the problem that you are trying to address, the questions that you're identifying that your model is going to answer, all of that is focused on helping the service users. That's the whole point of you doing what you're doing. Any applied research work is ultimately to help the people that are going to be using the service. So what does this look like in modelling and data science projects, for example? And again, no right answer with this, but some of the ways in which you could actively involve service users in projects is things like including service users in discussions about project ideas. You could have service users as part of your project mapping team. You could, process mapping team. You could encourage service users to contribute what-if questions. Have them think about ideas about how you might solve this problem. You could make them part of your core project team and provide feedback at all stages of your modelling cycle. You can encourage the service users to spread information via their own networks. They have amazing networks of patient councils and other groups of people that they like to be actively involved with that can really help you achieve what you need to achieve. And you can also, and this is really important, ask service users to give them drafts of stuff that you are conveying. That might be a report, or it might be a paper, or it might be even a model, a web app that you are developing for your model. Give it to them and say, as somebody that's not doesn't understand the technical details, as a layperson, is this clear? Can you understand this? Do you understand the outputs that it's generating? Because ultimately, you're going to be giving this over to people that have not been trained for 6 months in Python and discrete event simulation, and they may be more familiar with some of the aspects of the system, but so are your patients. And so making sure that they're aware, you're aware of how this conveys to a lay audience is really important. How might you go about recruiting them? Well, there's different ways you could do it. You could approach patient councils or groups within your organisation. I suspect you have some form of representation, or even some form of national group. You could look at contacting local support groups or charities or community groups if people are interested in being involved. You might advertise on social media. You might approach schools and colleges. Depends on what you're doing, really, in a lot of cases. But think about who the service users are and how you might be able to use existing networks to link in with them. And you should also be really clear when you do that about what the contributions are that you're expecting them to make. People should be very clear about what their contribution should be, and that you minimise wherever possible any accessibility barriers. That you make it as easy as possible for people to be able to contribute in the way that you want them to contribute. You should also be really clear as well about any reimbursement. You should at least cover any expenses they might incur. If you want them travelling in, 2 days a week to your office, then you're going to have to pay them travel costs. You can't expect people to do that for free. But sometimes there's additional funding available. You may consider reimbursing them in other ways as well beyond that. So to help you think about this, we PenArc, which is our organisation, we've got a dedicated patient public involvement and engagement team who basically support researchers to try and do more of this. So support people like our researchers within our team and other teams, and more widely. They have lots and lots of excellent resources on their website, and there's a link here which gives you that kind of advice about how you might go about doing this kind of thing. And there's also contact details. They're always very happy to chat through ideas. We've had HSMAs before who've turned up to some of their clinics. They put on these little regular clinics where you can just go and have a chat with them, and they'll give you some ideas about how you might approach things. So do check that out, and do if you're interested in exploring that, then I'd advise having a chat with them too. Okay, so I'm going to stop talking now, and finally, they say, goodness me, it's been nearly 2 hours down. So I appreciate that was a lot of information to take in this morning, and as I say, you're not expected to remember all this, but hopefully this gives you a bit of a feel for the sort of things that you're going to need to think about when you're designing your models, thinking about what your projects are going to look like. So you're now going to go off and into your peer support groups, and you've got a little exercise to do here. And you've been given a PDF, so in the materials you've downloaded from the repository today, you'll find a PDF in there called Exercise 1 PDF that provides an overview of a problem involving an eye clinic. Not an entirely fictitious problem, I should say. In fact, fun fact for you, this is a real problem. I've made up a couple of little minor details, but largely real problem that was undertaken by one of our first ever HSMAs. Indeed, Joe from Cornwall was looking at this project, and was the first HSMA I ever mentored on the programme. So it feels like a nice fit. So this is a real world problem. And what I want you to do in your groups is to read through the problem. I want you to identify what the what-if questions are that this eye clinic you think want the model to answer. I want you to then build a process map of the base case system, what's happening now as it's being described. I want you to build an interest-influence diagram based on the stakeholders you think you'd need to potentially involve for this project. And also a sort of broad outline for how you might involve patients and the public. Who might you involve? How might you go about doing it? And what would you have them do in this imaginary project? And you're going to put all that into a short 4-slide presentation. And when we come back, I'm going to ask a couple groups to present. So a couple groups at random. We're going to randomly pick. So make sure you've got somebody ready to present. And those that we don't, obviously 8 of the groups won't present. I will ask you to post your presentations in your Slack channel so we can have a look at them. So we're running slightly over, but I'm still going to give you the amount of time to do this. I can shorten the next section slightly, that's fine. So we'll give you 45 minutes, and within that I'd advise you taking a break as a group, either start or end or whenever you like. Just make sure you do take a bit of a break, because you don't want to be overwhelmed by this. But we'll have a 45 minute break now. So if we come back at 10 past, I'm just wondering actually whether. Yeah, I'm just wondering. No, let's keep it 10 past. I can always go through the other stuff a little more quickly. Keep it to 10 past. So we'll resume at 10 past 12. I'll ask a couple groups to present, and then I'll very quickly just rattle through some of the other bits. Okay. Any questions people have about any of that? No. Good. Okay. I will stop sharing. I'll open up the breakout rooms, and Sammy and I will bounce around. Please, as ever, largely ignore us. We're just listening in. But obviously, if you do need us for anything, then do shout. Okay, let me stop sharing and let's open up the rooms. Hi everyone, welcome back. So, I managed to get around to most of the groups, not all, but managed to sit on some really fantastic conversations going on with this exercise. Really good to see some really interesting discussions. I particularly liked the comment from one of the groups. You can tell this is an NHS problem because it's really messy and makes no sense, and that's so true. So I thought it worthwhile giving you something that isn't as nice as patient comes in, gets triaged, and sees a doctor and leaves, and something a bit more representative of real world. Interesting. I was a little bit devious because actually the problem that you are trying to process map here ended up being modelled as something which we call a governor model type approach, which we won't touch on in the course, but Sammy's got some materials that which you'll link to around that. And it's basically where you, rather than a kind of linear process, you have a kind of governor that works in your discrete event simulation that then chucks people out to various things like you go over and have that test done now and that kind of thing. So, but don't worry about the details of that for the moment. The point was to get you talking about the process, what you might capture, and some of the what if analysis. So, because of time, because we're running over slightly, I'm only going to pick one group for this, just to give their overview. But if I can ask everyone to post their stuff on the PIS support group channels, if not, because it's great to see there's some really good stuff that we saw. So in order to pick which group, and don't worry, you'll all have a chance to potentially contribute today, we are going to wheel out, pun intended, I think, we're going to wheel out the Wheel of Names, which is an HSMA feature that is much loved, certainly by me. Here is the Wheel of Names. You can access the HSMA 6 Wheel of Names from the bookmarks on the HSMA Slack workspace if you want to spin this wheel and pick a random group should you wish to see my face circulating for all eternity. You can do that. So we are going to use this to pick which group is going to present now. So let's spin the wheel and see who's drawn the short straw. Let's see who it is. Ooh, I think it might be Motorola. Yeah, it's going to be Motorola 68,000. And we have applause even to here as well. So let's close that down and I'll stop sharing. So Motorola, does somebody from Motorola want to share their screen?
Yeah, I was really hoping Motorola wasn't going to land there, but
Okay.
I'm afraid. Yeah, I give it a go. So we did start with we did get to quite a big list of what if questions, and we thought we could go on for quite a while, but we thought this was the main two questions that the clinic were wanting answering or exploring. So what if we employed a specialist nurse in the doctor's clinic? The first one. And what if we job plan the doctors so that they work in the clinic only and not on call? Yeah, so the next slide. So we start with the patient arriving at the eye clinic, the triage by nurse. It's a decision about whether the urgent care is needed. If no, they go to the nurse treatment room. Nurse treats the patient and the patient is sent home and leaves the clinic. If they do need urgent care, they go to eye casualty. The doctor examines the patient, and then there's another question, another decision about whether tests are required or not. If no, the doctor makes a diagnosis, and then there's a patient outcome, whether discharged or they're admitted to hospital, and then the doctor writes up the notes, and they're admitted to hospital. If yes, a test is required, then it's whether they're needed in the visual acuity test or ophthalmic imaging. We added here about whether there's external demand on this and how this may affect modelling. So if they go to the visual acuity room, then we have the optician performs a test, and the test results are sent back to the doctor, and the doctor makes the diagnosis. Similar for the ophthalmic imaging, the imaging technician performs a test, and then the results are sent to the doctor, and then they make a diagnosis. Okay, so on to stakeholders diagram. So we've got here high influence and low interest, divisional management, finance, exec boards, IT department, high influence, high interest, the service manager, administrator, clinical lead, and patients if there's a good PPI involved. So we discussed this a little bit, and we thought if there's not good PPI, they may be in the low influence, high interest group. Like there's a big impact on them, but they have little say in how things are operated there. And then we've got low influence, high interest. We've got performance, information, and ICB. I don't know if it's just because we was running out of time, but we didn't get any low influence, low interest group. Or if that's just because we couldn't think of any, I'm not sure. And then you can see we really ran out of time here. So how will you involve patients and who will you involve? So we thought a PPI group could be recruited from the waiting room. We could have like kind of leaflets in the waiting room advertising this role, or like, posters, something similar. And then this would be, please do, jump in, anyone else in the group, if you want to contribute to this bit. But I think the idea here that it would be like quite open, that we would have like patients telling us what they thought, rather than us kind of like the kind of management directing things. And like, so kind of think, and because they might have thoughts that we haven't even occurred to us, or they might have feelings that we kind of predict that they might think or expect maybe that they might have, but are actually quite different in reality. Okay, I think that's it.
Thank you very much. No, really good. Don't worry. I think it was a pretty ambitious task to get through. Quite a bit to try and get through there. But some really interesting thoughts that you had there. Interesting, you didn't pick up on anybody from the low interest and low influence. I think probably that's the hardest group sometimes to pick up, because we automatically think of people who are invested in some way, and so it can be difficult to think about those who are less interested but potentially could become more interested. So interesting one there. Interesting as well. I think all the groups found the system seemed to get into a bit of a mess when you got down to the testing thing. That's interesting in itself. How you would translate that into a model, and what you would then model to try and pick that, because you wouldn't model everything you've put there. But yeah, it's a really interesting dilemma. But hopefully gives you a bit of a glimpse into what sort of mess you might end up having to try to capture. Just talking about that mess can help. To say, well, that's crazy that we're doing that. I remember the bladder cancer project. I remember that project. They discovered during a process mapping session that the nurses were calling people on the telephone to let them know they had cancer. And they said that can't be happening, and they immediately stopped that. But it was really interesting that just having the people talking and realizing what was going on, they worked out why that was happening, and then they made sure that wouldn't happen. So there's some really interesting stuff that can come out of just trying to unpick a mess. So it's a really important stage. Brilliant, thank you, fantastic to see that, and fantastic to see all the great discussions. And as I do post your various bits in the peer support group channels, it'd be great to see those. Okay. So we've just got 10 minutes for lunch, and we are not going to delay lunch, because it's important that you all have an hour, and B, because my cat is already clawing at the door. I ran to the loo. He barged the door open. He is not waiting any longer for his next round of treats. So this will be a 10-minute, very quick run through of the last bit that I just wanted to mention. And really, I'm going to. So I will rattle through this. You can obviously look back in the slides, but there's some key points I just want to really reinforce in some of this stuff, because it's going to be important, particularly moving forward into some of the other stuff we're going to cover. So let me share my screen again. We don't want to see that now. We want to go back to the slides. Here we go. Right. So I'm going to rattle through this by going to this point here, because I've already sort of mentioned this a little bit earlier, that when we looked at that first example this morning, how long a patient spends in ED, well, very commonly we're given average figures. Well, it's about every 5 minutes or every 8 minutes they turn up, or they spend about 2 minutes with the nurse, and that's great. You need those kind of figures, but you don't want to plug those in as fixed amounts into a model. Indeed, if you do that, you'll end up in some very weird situations where patients are spending exactly 5 minutes with the doctor, and what you'll end up with will not represent reality, and you could be way off in terms of your outputs. And the reason is because you're not accounting for real world variability. Okay, so a patient may well arrive on average every 5 minutes, but that doesn't mean that every patient turns up every 5 minutes on the dot. So why would you model that? You're not going to model something like that. That's not true. That's not what happens. Similarly, a patient might spend an average of 5 minutes with a triage nurse, but that doesn't mean that the nurse has a stopwatch and, once the 5 minutes are up, they kick them out. Or if they only spend 2 minutes, that they keep talking because they've got to fill up their 5 minutes. It doesn't work like that. Now, there may be some processes in some bits of systems where there is a fixed time, but it's going to be relatively rare. Okay, so in most cases there will be variability, and even where things are supposed to be fixed, so something that comes close as like a GP appointment, have fixed slots, but you'll still get variability. But doctors will still take a little bit longer or a little bit shorter with various patients. You're still going to have that variability in there. And real life is full of variability. So if we're going to try and make our models as accurate as possible, to answer the questions that we need them to answer, we need to account in some way for that variability. And the way we do that is using something called probability distributions. And these are really, really important when you come to do modelling, and we'll be covering them a lot within discrete event simulation in particular. So basically, a probability distribution is just a way of trying to represent that variability within your data. So you basically, on the x-axis, you plot the values, and on the y-axis, you plot the probability of that value occurring. So the x-axis might be time spent with a nurse, and the y-axis would be the probability that a patient will spend that amount of time with a nurse. And that typically is based on what's happened historically. So you can then use these probability distributions in your model, and the model will sample every time it has a patient that's going to go and see the nurse. It'll say, right, let's sample from this distribution. So it'll obtain a value, and it'll pick a value randomly such that values with higher probabilities are more likely to be picked. But similarly, you could still have a value with a low probability being picked. So you might have, most patients are about 5 minutes, or between 3 and 6 minutes at least. But sometimes you can get a patient that 20 minutes, 25 minutes. That can still happen in your model, but it will be much rarer, as it would be in real life. So we use these probability distributions so that every time a patient comes in and has an interaction that we need an activity time or an interarrival time, whatever it may be, we sample, we randomly pick from the distribution what value it's going to be, and the probability of each value determines the likelihood of that value being picked. Now, I said this would be based on historical data, and you can create your own distribution that is precisely based on your real world data. So you could take your data of the last 2 years, 3 years, or whatever of time spent with nurse and plug that in as a distribution. That's known as an empirical distribution. Typically, you don't want to do that. You run into a problem known as overfitting, where the issue is that in using any distribution, you are making an inherent assumption that that distribution represents all patients that have ever been or ever will be, okay, in this version of the system. And you're saying this is the true shape of your probability distribution curve. Typically, your data, if it's based on historical data, will not have that kind of information in there. It's very rare that you have access to all the information that has ever been. And even if you did, things have probably changed significantly in your system. So what's more common is to use something known as a named distribution. And a named distribution is basically a particular distribution that has a certain shape and various other characteristics, a particular range, particular skew, etc., and which we define by giving sometimes no parameters, but sometimes one, sometimes two, sometimes more. And where there are parameters, we use our real-world data to define the distribution, to make our version of that named distribution. So basically what you're trying to do is you're finding a pre-existing distribution that resembles the kind of shape of your real-world data, and then you plug in the numbers you need to make the version for your particular data. So, example, an exponential distribution is typically used to model the time between discrete events that are happening continuously and which are independent from each other and at a constant rate. That means that in discrete event simulations, very often you will use an exponential distribution to represent inter-arrival times, the time between one patient coming in and the next. And so the model will say, I need to work out when the next patient is going to come in. It will sample from an exponential distribution to do that. And the exponential distribution takes a single parameter, which is known as lambda, and basically lambda is just 1 over the mean. So if you know that patients are arriving on average every 8 minutes, you can say, okay, well, I'll represent that as an exponential distribution, and my lambda value is 1 over 8. Okay, so then that fits your data. So you're basically making an assumption saying, okay, I believe this is representative of our data if we had access to everything that ever was and ever could be. And it turns out there are kind of common distributions that you tend to use for discrete event simulations for different things. And the two most common are exponential, which are typically used for inter-arrival times, and log normal distributions, which are typically used for process time. So for your activities, time spent with nurse, time with being treated, all that kind of stuff. Those are the two. Most models, if in doubt, use those two, and they will be the most commonly used. Now, a little extra tip, the exponential distribution is a lot simpler than the log normal distribution. And so a nice little handy tip, we'll come back to this in the discrete event module, is you can just start when you first create your first version of the model, just make everything an exponential distribution, because you can just plug in, all you need is a mean, because lambda is just 1 over the mean. So you can just say to people, okay, well, how long on average are they spending with a doctor? Plug that in. It's very easy to then adjust things and just get a feel for it. Then when you're happy with the model, you can then upgrade your activity times to a log normal distribution. And in the discrete event module, we'll show you how you can do that. There are other distributions that you could potentially use as well, which I won't go into detail here. The normal one's easiest to understand, but isn't particularly useful because it often generates negative values, which for activity times obviously can't happen. So exponential and log normal are the two most widely used, regardless of your particular problem. And then I've got 1 minute left, so I'm just going to very quickly rattle through this. Validation and verification, I would advise you to look through the slides for this, but basically this is all about checking how good your model is. Validation and verification are similar but different. Validation is basically working out whether your design for the model, your way of representing the real world, is sufficiently good to answer the question, to meet the objectives, whatever you've laid down. Verification is making sure that basically whatever design for the model you come up with, you've turned that correctly into a mathematical, or more likely in this case, a computer model. So in other words, verification is a bit like saying, okay, well, this is how I'm going to design my model. Have I coded it correctly? Whereas validation's about, okay, well, how good is this model that I've designed and built at actually being able to represent the real world? And very often the simple approach for black box validation, for validation, is to use black box validation, which is just so you say, okay, well, I'll look at the real world, I've got the data for that, I'll now run the model for the same period of time and see if the results are the same. It's a good start, and it's all right, but the problem is there are a lot of issues with black box validation. It ignores everything that's happening in terms of the inner workings of the model. You can't validate a what-if scenario because they don't exist yet. That's the whole point of you designing the model. And often the real-world data may be problematic itself, so it may not be the best thing to compare it against anyway. So it's a good start, but a better approach is to try and validate smaller parts of the model. Say, okay, let's look at the triage process. Is that an accurate representation of what's happening, etc.? Rather than just chuck everything in and say, right, we've got this many patients over this amount of time. Do the results come out the other end looking about right? Yeah, brilliant. Okay, model's valid. That's not necessarily how it works. It's also really important to bear in mind that it's not possible to prove that your model is valid, but you can disprove that it's valid. And actually, validation should be thought of as a kind of confidence building exercise. You're basically trying to instill confidence in the people you are building this for and yourself that it is sufficiently good to answer the questions that the model was built for. And the threshold for being confident in a model will vary according to the user and even the modeler. That does mean that you may have a valid model that is very good, but it doesn't say what they thought it would, and so they don't think it's credible. And you need to do more to build trust in what you've built. And similarly, it can work the other way around, where you have a model that is a load of rubbish, but it gets trusted by users, and maybe they've misunderstood some of the limitations, and you haven't conveyed that correctly. Very often, that's down to, again, what people want it to say. If a model says what they want it to, you will find very few questions asked of your model. That's not necessarily a good thing. You want questions asked of your model to make sure that you can build that confidence. And again, don't fall into that trap of thinking you need to chuck everything in there and it'll make it more valid, because that's a nonsense. Last point, just before we break for lunch, is one of the ways in which we can be wrong in our model is around parameter uncertainty. So we've just talked about distributions, so we use that as an example. Let's say we wanted to use a normal distribution. You won't do this in real life, but imagine you used a normal distribution to represent the process time, like time with nurse. Normal distribution, you define two parameters. You say the mean and the standard deviation, which are obviously really easy to interpret. Now, it could be that the mean and the standard deviation that we use to define the distribution we're going to use for our model, that's going to be derived from real data. We're going to, or an opinion, or a combination of both. That means that the estimates, the numbers we're plugging in to define that distribution are themselves based on samples that contain uncertainty. It could be that we've got a sample for the last 2 years and the mean time with nurse is 5 minutes, but actually if we looked at it over the last 5 years, actually the average is more like 7 minutes, okay? Or it could be we've got completely the wrong type of distribution, or because something changed in the data. There's always going to be uncertainty in there. So one approach to try and tackle that, try and get more data, but do you know what, that isn't always possible, and that in itself brings longitudinal issues in that, okay, well, we can grab another year's worth of data, but you know what, COVID happened, so that's not going to be representative, that's going to skew the results. So there's going to be all sorts of things that are going to muddy the waters there. One really easy solution that is really effective, though, is to do something known as sensitivity analysis. So sensitivity analysis, it's just a really simple approach that you can use to say, okay, do you know what, in our model, here are the results. In our model, we assumed that we plugged in a mean of patients spending 5 minutes with the nurse, and we based that on the data that we've got. You know, people seem to say that felt about right. But we also did some sensitivity analysis, and what we did with that is we tried the model if the mean was 4 minutes, or the mean was 3 minutes, or the mean was 7 minutes, and we observed what happened to the results. So if you change one of those parameters and it doesn't really change much about the results, and you can say, well, we might be wrong about that estimate, but it probably doesn't matter. It's not going to change the overall conclusions that we're drawing. If, however, you change something a little bit and you get a massive change in the results, then that's potentially more problematic, because that indicates that the results of your model are highly sensitive to the assumption that you've made about that particular parameter value. Say, well, look, if we're even a little bit wrong in terms of how how long a patient spends on average with a nurse, those results go out the window. And the important thing is, you may not be able to do anything about that, except you can convey that when you can convey the results. So people who are receiving the results need to understand that that's what's happening. Okay, apologies, I rattled through that, but I wanted to really convey those concepts of distributions, capturing variability, which you're going to encounter a lot on this course, and this idea of sensitivity analysis, which is a really neat way that you can just check for a bit of uncertainty. But as I say, have a look back through the slides yourself, which has a little bit more information on there. And again, all this kind of stuff will make a bit more sense when you start actually doing the model building too. Okay, we're going to stop for lunch there, and I think we'll still have the hour, so we'll resume at 1:35. We've got lots of buffering this afternoon, so we can easily make those 5 minutes back up. So go and have lunch, go and have a nice break now for an hour, and I'll see you at 1:35. You can remain on this call. The call will remain open. Just make sure you're muted and your camera's off. And just to warn you, 10 minutes before because we've got a different session this afternoon, you'll get a new splash page and music will start blaring out. So if you've got speakers set up in your office, just be aware of that. or at the very least, don't jump 6 feet when 25 past one comes around. Okay, brilliant. See you in an hour. See you, everyone.
This is an invitation to programming, developed for Atari Incorporated by Program Design Incorporated. Lesson 1. This is an invitation to programming. This series is designed to teach you how to make the Atari computer do things for you. You don't have to know a thing about computers to use this series. You are probably already familiar with some of the things the Atari computer can do. You won't learn how to make the computer do all these things now, but this demonstration cassette will teach you the following things. How to write simple programs. How to do math. We'll also demonstrate how to change color. How to do simple sound effects. Even how to do simple graphics. After using this set of demonstration programs, you can go on to use the Atari Basic Book. This will teach you the basic language in more detail, and you will be able to learn more complicated tasks. But for now, we'll keep things pretty simple and just help you get started programming your computer.
Hello everyone. Okay, so welcome back and welcome to this afternoon session on an invitation to programming. So we're going to be talking about principles of programming this afternoon before we start on our hands-on coding journeys from next week. And as you may have seen there, I want to give some thanks to my programming teacher way back 39 years ago when I was 4 years old and learnt to program using this wonderful thing here, an invitation to programming. My very first computer, the Atari 800 XL, amazing computer that taught me to do so much. And it came with 2 cassettes. I remember this. Yes, we used to store our media on cassette tapes. The first being a game called Pole Position, which was really good, and then the other was this inviting and quite mysterious cassette with this black inlay with this rainbow-coloured logo, inviting me to start my programming journey, and took me through the basics of coding and the principles of programming, and indeed. That's how I learnt at a very young age the basic core principles of programming. It may be 39 years on now, and we're using Python rather than Atari Basic, but nonetheless, a lot of the core principles remain exactly the same as they always have been. And so a lot of what I'm going to be talking to you about today is actually directly inspired by the way I was taught to program using that cassette tape and that nice American lady who was talking there on a slightly muffled audio cassette really was ahead of its time. This little utility. So just a nod there to my own programming tutor. So let's start by talking about what programming is, because virtually everything you're now going to do on the course will involve coding with a couple of minor exceptions, but most of the stuff you're going to be doing is going to be Python based now. And so we need to explore programming, and some of you may have a bit of coding experience. A few people have got Python experience before. Some have done a little bit in R, although as you'll find out, I think R is a little bit different in fact, quite significantly different in many ways to Python. Some have got some coding experience in the distant past. Maybe some of you watched that video. Maybe even some of you let us know if anybody else remembers that cassette and had that same invitation to programming, which they gloriously accepted. But nonetheless, we're going to assume from first principles that we're going to that you are new to coding, because even if you aren't new to coding, it may be worth going over some of these basics just to make sure we're all on the same page. So let's think about what programming is at a fundamental level. Basically, computers are stupid inherently, and they simply carry out a series of instructions that are given to them by us, by the user. And instructions are just a series of steps that the computer will work its way through. And programming languages basically are a way in which we can communicate with the computer to give it those instructions. And we use those programming languages to form computer programs that basically bundle up those instructions and will run through all of those instructions in turn when we run the program. So we write all the instructions we want it to do, and then and that's our computer program, and then we run the program, and the computer will go through step by step and carry out those instructions. And at a fundamental level, that's exactly how programming languages work now, in the same way that they did 39 years ago as well. So let's talk a little bit about computer architecture, because it's quite important to understand when we're coding. Basic computer architecture is that we have one or more input devices. Those are things like keyboards, mice, trackpads, webcams, whatever it may be, that are used to issue instructions to the computer in some way. And we have a CPU, a central processing unit, sometimes just referred to as the processor, which interprets the instructions that we give it, and it will execute them. So that's really the kind of beating heart of the computer. Of course, in the old days, that processor was very, very slow, and would only be able to churn through instructions quite slowly. Nowadays, we have processors that have multiple threads, so processors can perform lots of instructions in parallel at the same time, and perform these huge amounts of different things all simultaneously. But the principle's the same. We also have memory. So memory is used to store the information that might be required later, either in the short term, which is RAM, random access memory, which is where we just need to store some information for the moment whilst our session is active, but we don't need it retained, or we store it longer term in some form of storage, like a hard drive or a USB drive, whatever it may be, that will then retain that information, like saving files, etc., that we can load back up even after we've restarted the computer. And then we've got one or more output devices, things like monitors, speakers, things that will the computer will use to communicate back to us the outputs of the instructions that we give it. And it's worth saying something about the difference between low and high level programming languages. So low level programming languages are languages that run very, very close to the architecture and the specific architecture of the machine. And the lowest form is machine language, which is a kind of language in which you speak effectively directly to the hardware within your computer. And that used to be more common in the old days. People would use machine language in order to write close to the metal. They would effectively be issuing instructions to say, I want this processor to move that number over to this register, and now I need you to move it over there. Really sort of low level stuff. Machine language is not for the faint of heart. It's very, very complicated, and it requires us to give these really hardware level instructions to the user. You'll be pleased to know we don't do machine language here, as most people don't these days, at least for end use, like things like modelling and data science, we certainly don't. And so instead we use higher level programming languages. So these are languages that effectively strongly abstract from the details of the computer. We don't need to worry about how our particular computer and our configuration is. Things further down the chain worry about that. And instead, we can communicate with the computer via the programming language using what I would say is natural language, or things that are closer to natural language. Something that you could, I could give you a piece of Python code now, even if you've not seen Python before, and you probably wouldn't understand most of it, but you would at least be able to get the gist of some of it, because it will use actual words, and you would be able to say, okay, well, that seems to be doing something about input or whatever it may be. So you'd get some sort of sense. and it makes it much easier for us to interact with a computer. So examples of high-level programming languages, things like BASIC in the old days, C and C++, huge languages, Java, and of course Python, and there's many more. It's worth flagging up that Python is actually quite an inefficient language, and is actually, there's a lot of low-level C stuff that's going on. C is a much more efficient language, but Python is much easier to use, particularly for scientific purposes. So we sacrifice a little bit of efficiency to get us some other gains, and in reality, for a lot of the stuff you'll be doing, it doesn't matter too much, because computing power is so significant these days. Certainly much beyond the 64 kilobytes of RAM that I had to play with in my old Atari. So let's talk about one of the first things we should always talk about whenever we talk about programming, a central concept in any programming language, and that is a variable. And you'll hear non-stop about variables when you hear about programming. You'll be using variables right from the get-go when we start coding. You'll be using them all the time. So variables, basically, when we're programming, we often need to store some piece of information for use later in our code. And we store that information typically in the computer's memory. There's some things that we would store in longer term storage, but generally speaking, we store some information and say, remember this, I need you to remember that bit. And we store that information into boxes, effectively, and these boxes are variables. And basically, each of these boxes, each of these variables, has a name which indicates the information that it is storing, and it has a value, i.e. the thing that's inside the box. Okay, so we might have a variable called name, and the value in that box might be the string of text Dan. We might have a variable called number of modules, and it might store the value 5. We might have a variable called HSMA tutor, and it might store the value true. So effectively, each variable, you have a name for it which describes the information it's storing and the information within it. And because there's lots of different types of information that we would store, then variables similarly come in all different kinds of shapes and flavors, and these are known as variable types. And so there's lots of different types of information that we might want to store. So we might want to store numerical data, that's quite common. And we have things like integers, which are whole numbers, floating point numbers, which are basically just numbers with decimal places in them. There's lots of other different types of number that you use, but commonly, for most of the stuff you'll be doing, integers and floating point numbers will be most of what you use numerically. There's also text variable types, so things like characters, which are individual letters, numbers and symbols, and strings, which are sequences of those things. We'll come on to this when we get to Python. Actually, Python is a bit unusual in that a lot of programming languages have a separate type for a character and a separate type for a string. Python doesn't do that. It has no concept of a character. A character is simply a string of length 1. So it doesn't have this differentiation, but it's worth knowing that those things do exist in other languages. We also have booleans. So booleans are really useful types of variable, and they basically just store a value that indicates if something's true or false. And typically we use the words true or false. Sometimes you can use ones and zeros, 1 being true, 0 being false. But basically it stores one of those values, and they're really useful when we come on to conditional logic, which we'll talk about more in a moment. Then we've got things like collections. So these are things where we want to store more than one piece of data within our box, within our variable. And so we have things like lists, which are ordered sequences of things. So we might have a list of numbers, we might have a list of strings, we might have a list that includes numbers and strings and booleans in the same list. But they are in an order, so we can say the fact that that's the third element in the list matters. And then we have things called sets, which are similar, but they are unordered, and they only contain unique values. And that's why the order doesn't matter, because everything in there is unique, so we can just refer to the value itself. We have things called dictionaries, which are, again, unordered, so the order doesn't matter. And the values are essentially pairs in which you have an index and a value associated with that index. So you can look something up. So you might have a dictionary that stores various information about a patient, for example, and you might have the index being name and then the value being their name, index age, the value being their age, and things like that. And you'll see some examples of dictionary usage when we get into Python. There's also something called tuples. Tuples are like lists, but they can never change. They're not widely used, but there are certain times that you have to use tuples, particularly for machine learning, and you'll see a few examples of that throughout the course. So I've just talked about the fact there are different types of variables based on different types of information that they can store, and some programming languages are what's known as strongly typed. So you may hear that about language. It's a strongly typed language, and what that basically means is that if you're in a strongly typed language, when you create a variable, you have to say not only what its name is, and you might give it a value to start off with, although you don't have to. Sometimes you can just create a variable and leave it empty for a minute. But in a strongly typed language, you also have to say what type of variable this is, i.e. what sort of information it's going to store. So if you have to say, well, I want this to store integers, or I want this to store strings. And a strongly typed language then won't let you put anything else in there. So if you say this is a string and you try and put a number in there, it'll say, no, you told me this was a number. Now, I flagged that up because Python is not strongly typed. So it is not one of those languages. You do not need to declare what type of variable it is when you create a variable. You simply say, this is the name of my variable, and you assign either an empty value or the initial value you want it to be. If you chuck in a different type of variable, so let's say I have name, I call my variable name, and I say it's got a value of Dan. If I then overwrite that and say I want name to store the value 2 now, it'll say, oh, okay, that's fine. Name is now an integer then, and it just automatically does that for you. Now that has advantages and disadvantages. We are a Python-loving course here, so we are choosing to see the positive in that Python, how accommodating is Python to our needs, rather than it being a little bit more whimsical. Some people absolutely hate languages that are not strongly typed, but Python is not a strongly typed language, so you just need to be aware of that. If you are not used to coding, if you've never coded before, then this probably won't affect you as much, except if you then went to a different language that is strongly typed, you might find it a little odd. But just be aware that that is a particular difference of Python. So let's put everything we've just talked about together. Let's imagine we wanted to build a really simple calculator that just adds up 2 numbers, and we want to write that as a computer program. Effectively, what we would need to tell the computer to do, first of all, we need to get it to ask the user for the first number. So we need to get some sort of input from the user. Then we'd need to get the computer to store that first number that was input by the user in memory as a variable. Then we'd get it to ask the user for the second number. Then we'd get the computer to store that second number in memory as a variable. Then we would perform an addition operation on the 2 variable values. So we'd say the value you've got in that box over there and the value you've got in that box over there, add them together. Then you'd store the result of that addition in memory as another variable, and then you would display that result variable to the user. So it sounds long-winded, and it kind of is, but that's effectively what you would do. And you'll see examples of this when we get into Python. So worth talking a little bit about conditional logic next, because this is you're not going to go very far in your programming journeys without talking a little about conditional logic. Because very rarely are our programs completely linear. It is rare that we say we want you to do this list of 200 lines of code, and from start to end, and it'll always be this that we want you to do. very often we need to check whether something is true or not, and then do something different depending on what the result of that check. Okay, so a conditional logic, which is what that is, basically allows us to tell the computer, if this is true, then do this, otherwise do this. Okay, so it allows us to build in branches, which means we can think about conditional logic a bit like a decision tree. So as an example here of a decision tree, this is how conditional logic would work. So am I hungry? I'll check if I'm hungry. If I am, then I'll also ask whether I have cake. If I'm not hungry, I won't do anything. But if I am hungry, do I have some cake? If I have got some cake, then I'll eat the cake. Otherwise, well, is the shop open? If it is, then I should probably go and buy the cake. If not, then I will eat something else. Okay, so that's an example of conditional logic, where effectively you're going through and asking questions and then doing one thing if it's true and another thing if it's not. And of course, sometimes we may need to check more than one thing at a particular time. So it might not be a case of do this or do this. It might be a case of there might be multiple things that we want to do. So the question I might ask is, well, how many cakes do I have? If I've got 10 or more, then I can do nothing. If I've got fewer than 10, but I've got at least 5, then I'll add it to my shopping list. But if I've got fewer than 5, but I've got at least one cake, then I'll walk to the shop. If all of that is untrue, in other words, I have less than one cake, then I will be running to the shop. And so that's an example of where we can check against multiple conditions and do, in this case, 4 different things, depending on the outcome of that conditional logic. Similar to conditional logic, which allows us to branch our instructions and go down different routes, there's also a really important concept in programming known as loops. And loops are very, very useful because very often, as well as our programs not being linear and not wanting to do exactly the same thing all the time, very often as well, we need our computer to do the same thing a number of times. Okay. Now, we don't want to typically, let's say we wanted it to print a message to the screen 10 times, we don't want to have to write the instruction to print 10 times over. That would be pointless. So instead, we use something called a loop. And there's basically 2 kinds of loop that you'll use. The first is known as a for loop. So a for loop is basically where we say, I want you to do this bunch of stuff this many times. So run these instructions this many times, okay? And it might be a single instruction or it might be a whole list of instructions, but do all of that many times, I tell you. And then similar, but slightly different, we've got this idea of while loops. So while loops are basically saying, I want you to do this bunch of stuff, these instructions, and continue doing them until this condition it becomes untrue, becomes false. Okay, so keep doing this whilst this is true. And the second it becomes not true, then you can stop. Okay, so for loop says do it this many times. A while loop says keep doing it while this is true. And you'll use a combination of for loops and while loops depending on what you're trying to do. So let's talk about for loops first. Let's say we wanted our computer to add 2 sugars to our cup of tea. Then we could write a for loop here and say, I want you to do this up to and including 2, because we want to count the spoons of sugar up to and including 2. First thing, I'll check how many sugars have I added. It's fewer than 2, so I'll put the spoon in the sugar. I'll scoop, I'll add to the tea. These are our instructions that will go in the for loop. When I get back around, I now check how many have I added now. Well, it's 1, so it's still fewer than 2. So back round again, I'm going to put the spoon in the sugar, scoop, and add to tea. So I'll go around these instructions again. This time, I've now added 2, so I've met the number of times that we set up for the for loop. So I will now stop, and that for loop is over. And of course, we can combine the concept of variables with this idea of a for loop. So instead of saying, I want you to do this twice, what we could say is, well, let's ask the user first, how many sugars do they want? I'll store that answer in a variable, I'll call it X, and then I want you to do this set of instructions, putting the spoon in the sugar, scooping and adding it to the tea, I want you to do that however many times the user said. So I'm not going to hard code it. I'm not going to say it's always twice. I'm going to ask the user, which means if they said 0, that will never run. So that's for loops. While loops are a little bit different. So let's say we wanted the computer to sing to us until we fall asleep. So we want you to keep doing these instructions, user, whilst the user is awake. So I'm going to check, the first thing I'm going to do is a while loop. Is the user awake? Yes, it is. Yes, they are. So I'll clear my throat, I'll sing for 1 minute, and then I'll hit them over the head. Are they still awake? If they are, I'm going to go background again, and I'm going to keep going around and around and around until this no longer becomes true. If the user is no longer awake, then I will stop, and only at that point. And you will encounter, and we'll talk more about when we get into the coding, you will encounter things known as infinite loops, in which, and very often these are derived, they can be derived from for loops, but very often from accidentally coding something incorrectly in a while loop, where you get stuck and you can never exit because that condition can never become false. And that's the most common way it happens. Sometimes you want to deliberately make an infinite loop, and again, we'll look at examples of that as well. Okay, any questions about any of that? No? Great. Okay, so that's your first induction into coding. So before we move on and talk about anything else, you're going to go now into your groups and tackle your first exercise. So the famed company Chalk Showers and Baths Incorporated has approached you to ask you to design software for a new automated shower system, and it's called the Chalk Automated Shower with Genius Responses and Banter, otherwise known as the Cash Grab system. And basically in this system, the user steps in the shower, and then the first thing it does, the shower will ask them for their name, and it'll say good morning or good afternoon or good evening or whatever it may be, depending on what the time is. And then it waits for the user to say begin, and at which point the shower will then check whether the user has a previous perfect temperature stored. If they do, the shower will turn on at that temperature, and it'll remain at that temperature until the user says too warm or too cold. If they don't have a particular perfect temperature stored, they might be a new user, then the shower turns on at 30 degrees C, and the shower will continue to raise the water temperature by 2 degrees C every 5 seconds, up to a maximum of 42 degrees C. I've added that in this year because people pointed out that might be quite deadly if we didn't put some sort of limit on that automation. If the user said it's at any point that it's too warm, the shower will then drop the temperature by 1 degree C every 5 seconds down to a minimum of 16 degrees C. And if the user says too cold, then it starts going up again by 2 degrees C every 5 seconds. So it keeps going up and down and up and down whilst the user is saying too warm, too cold, etc. It continues doing that until the user says perfect, and then the system will hold the current temperature and it'll record it in a variable which it calls perfect temp alongside their name in a variable called user name, and it'll store both of those pieces of information in a list called user preferences. If the user had a previous perfect temperature, then if they step back in and record a new temperature, that new temperature will then overwrite that. But they can adjust the temperature in the same way, the only difference being that the shower will turn on at their previously stored temperature until a new one is stored. And basically the shower will continue to run until the user says end shower, at which point the shower says goodbye, followed by whatever their name is. Okay, so now you're going to go into your groups. What I want you to do as a group is to draw a diagram in any way you like. Doesn't matter how you can be as creative as you like on this. Draw a diagram outlining how the system will work in terms of how this will translate into a piece of software Thinking about the programming concepts we just talked about. So I want you to flag up where you think there'll be any conditional logic, any loops, what kind of loops they'd be, any places where you'd store variables, etc. And I also want you to, on that diagram, to write a list of the variables that will be used in the system, along with the type of each variable. So that the type of variable that it will store. We're not committed to writing in Python, so we may need to know that, and also a short description of what the variable is storing. Okay, so you write here's a variable called this. It'll store integers, and the variable you write a little description saying what that variable represents. Then if you have time, if you manage to do all this, and you still have time, I want you to propose some improvements to the system and then include those on your diagram, again, identifying any conditional logic or loops or variable storage within that. So I'm going to give you 45 minutes. Follow and make sure you take a 10-minute break before we come back as well. And when we return, I'll get a few of the groups at random to talk through their ideas. So everyone clear about that? Cool. I say Sammy and I will bounce around between the rooms much as we did earlier. I'll open up the rooms now, and you can go in and be as creative as you like. All of these instructions, again, you can find them on slides 18 to 20 of the slide deck. So have a look and read back through that and what we've just covered there. And as I say, if you get time, add in some improvements, because this is by no means necessarily a perfect system. Right, let me stop sharing and let's open up the rooms. Hi everyone, welcome back. So managed to get around again to quite a few of the rooms. Really good to see lots and lots of discussions, some really interesting ways you were approaching this. Excuse me. One thing worth pointing out, that there are no sort of right or wrong answers with something like this. This is really just to get you sort of thinking in a programming logic kind of way. So this is kind of the equivalent of you maybe scribbling some notes to yourself. This is probably not how you would approach doing a code. I mean, there are formal ways in which you can, proper software engineering where you can design. We don't teach that because we don't use it ourselves. But and for a lot of things you do, it's kind of overkill. But there are no sort of right or wrong ways really to approach something like this. It's really just to get you thinking in that right kind of way. And really that goes to the heart of, even when we get into the coding stuff. There are things that won't work, but there are usually multiple ways to approach a problem. So you may well find that whilst we'll have solutions and inverted commas for a lot of the exercises going forward, once you get into the code stuff, you may well have an alternative solution that will work just as well, maybe even better actually than the solution. So don't worry too much about that. There's a lot of this is creativity and getting you to think. So we're going to get a couple of groups just to present what they came up with. And I think you probably all found that it was a little bit more complicated in terms of the logic once you started to really think about it, how you might sort of convert this into code than perhaps it first appeared. So let's bring up the wheel of names because let's pick some people to for the presentations. Sorry. Right, so again, if anybody wants to look at the bookmarks, so you can access the wheel of names up here. So let's spin the wheel and see who we get. This is going to be close. Yeah. Oh, that's just an Zylog breathing a sigh of relief there, I think. But Denise, does somebody from Denise want to share the screen, talk us through what you came up with?
Hello, yep, I'll put it on screen. I think doing this exercise really shows you how complex coding really can be with what seems to the human brain not too complicated. So we've done it in draw.io, which again takes some getting used to. So we start with the user stepping into the shower. then the shower asks for the user's name, which will store for later. It then checks the time, and if it's in the morning, it will say good morning. If it's in the afternoon, it will say good afternoon. It then, I guess it could be a while loop, but we just put in if the user says begin, it checks if the user has a preferred temperature stored. If it does, it will use that temperature. If not, it will go to 30 degrees. And then it gets into the kind of web of chaos down here in this next bit. So whilst the temperature is not perfect, we want it to increase by 2 degrees every 5 seconds. We've kind of put this placeholder box for where we wait for the user. Obviously, it might be coded a bit differently, but it kind of helped frame everything. So it has a few kind of outcomes which are a bit messy. So if the user says it's too cold and it's below the max temperature, we want to raise it by 2 centigrade every 5 seconds, and then it will go back to the top. If the user says it's too warm and it's above that minimum temperature, we will drop it by 1 degree every 5 seconds. And then the two other kind of logic steps is making sure that if it does hit that minimum or max temperature, that it stops that going up or down. And then if we do finally get the user to say it's perfect, we'll then go through to the next step where it will save their perfect temperature and their name in a list. And then we hit a kind of the kind of ending part of the process, which is kind of why we've hit this very fun arrow going down the side. So if they've already got a perfect temperature. So whilst the user doesn't say to end the shower, we'll continue at that temperature. But otherwise, if they do, we only say goodbye followed by their name. So that's our process. In terms of the variables, these are the ones we came up with. So we got our name, which we've decided to be a string. The temperatures, so the perfect temperature, min and max, be an integer. The time that it might have to check, which we've given it a date time. Might be a timestamp in Python. And then we've got our user preference, which we save at the end, which we've given as a dictionary. We did quickly look at some improvements. So I guess a key one is we could just ask the user what their perfect temperature is instead of going through this ridiculous logic. We've got no idea around the kind of length of the shower. So I don't think at the start it kind of asks, considers if the person doesn't say begin. So, whether, it will shut off after a certain amount of time or possibly something like that. And, what if they never reach the perfect temperature? Potentially you could have some logic around that. Or some functionality, so go directly to a minimum or max. And yeah, that's what we've done.
Awesome, thank you very much. No, really good, really interesting the way. I don't wish to rain on your parade in terms of adding in more arrows, but technically, if the user had a perfect temperature, they can then disrupt it again. So you may have actually another web of arrows.
Yeah.
Where they go around. You'll be all pleased to know you won't be coding any shower systems in Python. And in fact, in reality, if you were doing this, you would have things that are known as triggers that would, the API would basically listen out for a trigger, and then that would trigger off the code. Trying to do it using, some while loops and stuff, you will get into a messy web of arrows in code as well. So brilliant, thank you very much. Okay, well we've got time for one more, I think. Let's get somebody else to share. So let's bring up the wheel again. Let's spin the wheel. See who's next up. It's not going to be Zilog this time, definitely. And we had Motorola earlier, so I'll tell you what. Let's spin that again because let's be fair and try and get somebody else. Motorola are relieved by that, I'm sure. It's going to be TIA. TIA. Does somebody from TIA want to share their screen?
Yeah. 1 second. So all the time I was thinking about this outside toilet from Bob's Burgers, but which was a very similar toilet thing with a toilet anyway. So we also used draw.io and did end up getting into a bit of a web of, but these can say too hot or too cold. Yeah.
You know, you're not sharing. Sorry, just to.
I'm not sharing. Oh, I've still got the, yeah.
There you go.
Got to double click the thing. So, yeah. So this is our diagram, also in draw.io. And we started, it was a bit hectic. It's all quite hectic, sort of going through all the different things. So someone shall ask the name, store the variable, store the name of the variable, look up the time, and then set the variable current time, which we've got as like a string of like morning, afternoon, evening. Say good morning, username, or good time. So then if the user exists, and if their perfect temperature exists, set the perfect temperature. And if not, set the current temperature to the starting temperature, wait for it to begin. And once they say begin, start the water at the current temperature. If that is the perfect temperature, then remain constant. If it's not, while the current temperature is below 42 degrees, every 5 seconds, increase it by 2. There's no user input, keeps going around. The user says too hot, while the current temperature is less than, is greater than 16, it will reduce it by 1 degrees every 5 seconds until the user says perfect, sets the perfect temperature, and then it remains constant until the user says too hot, too cold. And then it just keeps going around and around until they say end shower, says goodbye, stops the water, and goes back to the beginning of waiting until someone enters the shower. Some improvements we were thinking about, we could hold the steps up and down as variables so that if you don't want to, say 5 was too big a step to jump up, oh sorry, was it, yeah, whatever, you could set the variable to jump up there. If there's no perfect temperature set, then ask a starting temperature, because the user might know what temperature they want to start at, and 30 is quite cold. And it could take a while to get there. Maybe ask or store the age of the user to add more safeguarding features if there's a younger user. Some nice to have things, maybe have different voices, and an option to play the radio while you're in the shower. And also maybe have different temperatures if it was morning or afternoon. Install that inside the user dictionary.
Excellent. I really like your ideas for improvements there. They're really nice ideas. I like that. Interesting as well that you touched on something that I saw one of the groups at least pick up on, and that is that with the temperature, of course, your current logic, technically, you could end up at 43 degrees because we go up by 2 but down by 1, which could end up, if it's less than 42, you could end up at 41, and it would then increase the temperature by 2 degrees C, which would be 3. So again, and I put it in deliberately as a little bit of a trap. But yeah, it's all those kind of little things that you need to, and that's why sort of testing your code, etc., is so important to find out all those little things. But yeah, great, really nice, and as I love your ideas for improvements there in particular as well. Brilliant, thank you, all fantastic, and please do share those on your peer support groups as well. I saw it's great to see so many of you using draw.io. I've not used it myself. Sammy highly recommends it, and I can see why. I might, I don't know if it'd be useful for Sammy at some point to do a little sort of little intro guide or just even a 5-minute video just on using it, if that's useful. I mean, it's very easy for me to say that, to volunteer somebody else to do that. So Sammy's probably thinking, shut up, Dan. But if that's useful, it might be good, because it does seem like a nice little tool that you're getting to grips with. So I should probably use it myself as well. Okay, right, let's carry on with the next bit. share my screen again. That and move on. So let's now talk about functions. So functions are a really important aspect of any programming that you do. So often when we're writing things, writing our instructions to the user, to the computer, often there are things that we want to do that we will want to do quite often. And it might be that we want to do this more than once in the same code, in the same computer program, or it might be that we want to write something that will be useful for other programs that we have, or even for other people who may want to use the code that we've written. We basically want our stuff to be as reusable as possible, so that we're not having to write it out and sort of reinvent the wheel each time. And to do that, we can wrap a set of instructions in something called a function. And basically a function takes, may or may not take some inputs. Okay, so there are some functions that don't need any inputs, some that will take one, some that will take many. It does something, and if there are inputs, it'll do something with the inputs. And then it'll return optionally an output. It may return nothing, it might return something, it might return a few things. And the things that it does in the middle are just sets of instructions like you would write anywhere else in your computer program. And so we define a function by giving it a name, saying we want to call it this, and therefore whenever we want to run that bit of code, we can call it by name and say do this thing, and it'll know, okay, I need to do that set of instructions. We tell it the list of inputs that it should expect, if there are any. So if we define that it needs a name and an age, for example, as inputs, then whenever we say I want to use that function, we have to give it the name and age. We tell it the things we want it to do whenever we call that function, and we tell it any outputs that it should return, if any. As you'll see when we come on to look at this in Python, we need to do something. If we are returning stuff, we need to hold it somewhere. It's important to note the function does not do anything until it is called. So by calling a function basically means, in programming, it means I want you to run, you're giving an instruction to the computer to run that block of code that you have defined earlier. So, but when you define it, when you say this is a function called, add numbers, you tell it, give it a list of instructions that will add some numbers together, it won't actually do that until you tell it you want to run that function, until you call the function. So this is basically what we're talking about, that we have a function that has a function name, we have possibly some inputs, stuff that we want the function to do, and it'll manipulate the inputs in some way if we've got any, and then potentially some outputs from that function as well. So to give an example that might make this a bit more meaningful, let's imagine we've written a function called findMinimum that will take in 3 values and it'll tell you what the lowest one is and it'll spit that out as an output. So here we've got a function called findMinimum. We define there are 3 inputs, 3 numbers, and in the block of code, the instructions for that function say will basically first set the value of x, one of the inputs, to be the variable lowest. So it'll say, okay, well, I'm going to assume first of all x is the lowest. Then it'll check, well, is y lower than x? And if it is, well, then I'll set lowest now to y, and then I'll check z. Is that lower than my current lowest? And if it is, then I'll set the lowest to z, and then I'll return the value of lowest. And the return statement basically chucks out an output. So you'd call that function findMinimum with these inputs, and it'll spit out an output. So the thing it will give you back is whatever value is stored in lowest, which will be the lowest of these 3 values. So if we were to write that function in code, if we then called the function by giving it its name and this set of inputs, then that would return the value 2, because we'd give it 3 inputs, 3, 7, and 2, and if we worked our way through the instructions, that would eventually set 2 to be the lowest value, and that's what would come back. Okay. Also important to note, and this is particular to Python, so other languages have different ways of doing this, but Python, if you were listening closely to the Pep 8 song earlier, it's all about indentations. Okay, so Python, where you've got things like functions, we use indentations in our block of code. So this is an actual Python code for a function, and it basically we indent the body of the function, i.e. this is the stuff, all the stuff that is indented, tab indented here, so it's a single tab. We indent with the tab key, but when you use VS Code or most IDEs, it will do that for you. So when you write this line of code here and you hit enter, it'll start your cursor there because it knows, okay, you're defining a function, I need my indentation here. So then everything indented to that single tab is considered part of the function. So here we've got stuff that isn't in the function. This is an import statement. You'll learn about that next week. Here are some other statements that are not part of the function, but this is part of the function in here. So this won't run until we say that we want to run the my function until we call that function with 2 inputs. Okay, so that's the function declaration. This is the body of the function, and Python is all about indentations. So some programming languages use curly braces, for example, and you open and close with that. Python doesn't use that. It's all about indentation. If you're not used to that, it can be a bit weird because the formatting matters in Python. You can also have multiple indentations. So if you've got so for example, in a conditional logic statement where we check whether something is true or not, and then say if it's true, do this, that would again be an indentation. You'll see that again over the coming weeks. So you could have, if you had conditional logic within a function, then we'd be indented down to here as well. So you can end up quite a way indented in some of this stuff. Okay, so those are functions, and they're really important, and you'll be writing functions a lot during your programming time. Let's now talk about a slightly more complex concept within programming, but a very important one for any real modern coding. And I'm going to flag up right now that this is a concept that sometimes even people who are used to coding still struggle with. Okay, so this is, don't beat yourself up if this doesn't make sense the first time through. Also, don't beat yourself up if you find that when we come to it in Python that you're struggling to make sense of it a little bit. It is a slightly harder thing, but it is really important. And hopefully as we go through the course, you'll see lots of examples of this and why it's important. And this thing is called object-oriented programming, which is commonly abbreviated to OOP. And you'll often see OOPS as well, oops, which stands for object-oriented programs. So far, when we've been talking about programming, we've said it's a list of instructions that the computer follows line by line. And that's known as the procedural programming methodology. You do this, then you do this, then you do this, then you do this, etc. until you get to the end and then you stop. Now, all code technically does that, even object-oriented code. But object-oriented programming is a slightly different way to structure your programs, okay? So rather than effectively a list, a script of things to follow from beginning to end, in object-oriented programming, you center everything around objects. And those objects have things called attributes, which are variables that belong to them. And they have methods, which are basically, they're just functions, but we tend to call them methods when they belong to an object. Okay, so you'll hear functions and methods used interchangeably. It's the same thing, basically, but we tend to call them methods when they belong to an object. And objects are created from classes. Don't worry, this will all make a bit more sense hopefully in a minute. They're created from classes, and they are instances of classes. And the classes are basically generalized blueprints for how a certain type of object should work. Now, I appreciate at the moment you're probably thinking, what on earth are you talking about, Dan? Let's simplify this. Right, what's that? Shout it out, anyone.
Vehicle.
Say that again, sorry.
Vehicle.
Yeah,
Ambulance.
vehicle. That's a valid answer. Ambulance is also another valid answer.
It's a
So
digital image.
So let's first of all go with ambulance. Okay, so that is an ambulance, right? Let's say we wanted to write some code that defines how an ambulance works. Okay, there will be properties that an ambulance has. Okay, things like the trust it belongs to, the registration number of that ambulance, whether a patient is currently on board, whether the siren's currently going off. Okay, these are things that you've been used to using variables this afternoon. These are kind of variables that belong to the ambulance. Okay, you can imagine each of these things being a piece of information that the ambulance is carrying with it, if you like. And those things can change. You know, whether the siren's going off will vary according to, you know, whether somebody's turned the siren on or off. There will also be things, as well as the things the ambulance has, there will be things that the ambulance does. So the ambulance will be driven, the ambulance will park, the ambulance will have patients loaded into it or out of it. The ambulance will be able to have its siren switched on and off. Okay, so there's things that it has, pieces of information that it carries with it, and there will be things that it does. And in object-oriented programming, the things it has are attributes, and the things it does are known as the methods. And basically, you frame everything, or most things, in terms of various objects that have pieces of information attached to them and can do things. Okay, so everything kind of belongs to an object. So in object-oriented programming, we have this idea of a class. And a class is basically a piece of code that says, this is how an ambulance works. This is the set of attributes that it has. These are the pieces of information that it carries with it, and this is the things that it can do. These are the methods. Okay, and then what we can do is we can create instances of that ambulance class. We specify the blueprint being the class. That's what an ambulance should look like, and then I say, okay, I want one of these things. I want an ambulance, and I'm going to call it Dan's ambulance. And Sammy says, I want my own ambulance, and that's Sammy's ambulance, etc. Here we've got Dan, Sammy's, and Amy's. They've all got their own ambulances, and these are the instances of the class ambulance. Okay, so the class is like the blueprint. This is what an ambulance looks like. And these are particular instances of that class. And all of these ambulances operate completely independently. They're their own separate objects, and they can all do their own thing separately from each other. But the way in which they work is defined by this ambulance class. And this process of creating an object from the blueprint, from the class, is known as instantiation. Okay, because each of these are instances of this general class. So in our example, we might have a class called ambulance. It has attributes, things that it carries with it, information about it, and methods, things that it can do. And so its attributes might be, things like name of trust, which will store as a string, registration number will store as a string, whether the patient's on board or not, which will be a Boolean, whether it's true or false, and similarly with siren on, whether that's true or false. And there's things that it does, the methods. You can drive, and remember, a method is just a function, so we'd pass into that maybe a speed that we want to drive at, and that would be probably a floating point number. We might want to tell it to park, and perhaps that requires us to tell it where to park, and we pass that in as a string. We might have a method that tells it to load a patient and tells it who to load into the ambulance, and similarly to unload a patient, who to unload. And then we might have methods telling it to turn on the siren, turn off the siren, which we don't need to pass any inputs. It just says basically, okay, you can turn the siren on now or turn it off. So that's the class. That's how we would write the class. And you'll see when we come onto this in Python how you turn this into Python code. And then down here, we've got instances of that class. These are separate objects that are created from this generalized blueprint. So that defines generally how an ambulance works, the things it carries with it in terms of pieces of information, things it has, and the things it does. But down here, I can create lots of different instances of that class. So I can create Dan's ambulance, which has the name of trust, Chalk NHS Trust, this registration number, there's no patient on board, but my siren's on. And then Sammy can create her own version of her ambulance, which is from Rossa Healthcare with her own registration number. That one does have a patient on board, and she also has her siren on. But they act independently of each other. But the beauty of this is that we only have to define an ambulance once. And then we can have 2,000 ambulances if we so wanted. It doesn't matter because we've only had to define once what an ambulance is. And then we can just create lots of versions of that thing. So because they're separate, they can operate independently. So Sammy could go along, she could be driving her ambulance at 50 miles an hour, siren blazing, whilst Dan's taking a leisurely drive back after a long shift. He's just driving along at 20, turns off the siren, and then parks up at the base. So they're operating independently, but we've only had to define what it means to be an ambulance, what it means to drive, what it means to turn off the siren. We've only had to define that once in terms of the class. So I said that when we move from a class, which is the kind of the blueprint for what an ambulance should look like, to an object, an instance of that class, that process is called instantiation. And when we instantiate an object from a class, we use something known as a constructor. And a constructor basically defines what should happen when we tell it we want one of these things built. So I want a new ambulance built. The constructor will do all the work of putting it together. Okay, so it will do things like it'll specify the initial values, the default values for the attributes, the information it has. It might even run some initial methods that you'd want to happen the second you create a new object. And the constructor is itself a method within the class, but it's a special kind of method that in Python, which we'll see when we come on to that. And I won't confuse you, but it is effectively just a method within a class. So in our example, for our ambulance example, we might have our constructor set up the name of the trust and the registration number. So when we say we want a new ambulance, we, depending on what we put in the constructor, it might say, well, okay, well, we need you, when you tell us that we need a new ambulance, you'll need to tell me what the name of your trust is and what your registration number is, and then we can create that new ambulance. But maybe for every new ambulance, we say that the siren will always be off at the start and there's no patient loaded in. Now, object-oriented programming uses something known as the 4 pillars to create efficient code. It's a really important concept, object-oriented programming, in creating really efficient computer programs. And don't worry too much about the details of this, but this is just to flag up why object-oriented programming is so important. And the 4 pillars are known as encapsulation, abstraction, inheritance, and polymorphism. So encapsulation is the first one. So to take that, to give you an example based on our ambulance example, that basically says, look, the code that defines what an ambulance is and what it does is self-contained and it's separate from everything else. That's what encapsulation means. Abstraction means that someone that needs to use the code for an ambulance doesn't need to know all the technical details. That's really important because that means you can create a class that will do, it might have really useful methods and be able to do really useful stuff. Then other people can use that without having to worry about all the instructions that you've written. They can just know that this works and how you know, the various methods they can call, and you're going to be using that. This is the whole concept of abstraction is the reason why in a couple months' time I'll be able to teach you how to do things like build neural networks, because if we didn't have that, I would have to teach you the. In fact, no, let's correct that. I would be finding somebody who would be trying to teach you the very deep mathematics that goes on underneath a neural network. But you don't have to worry about that because there are packages of code that people have written that will deal with all the mathematics behind it. You just need to understand how they work so you can design them and build your own one out of these building blocks. Okay, that's why it's so important. We've got this concept, I'll come back to this one. We've got this concept of polymorphism, which in our example says, look, when I drive a car and I drive an ambulance, I say I'm driving, but driving an ambulance is a bit different to driving a car, okay? And then there's this fourth concept known as inheritance, which says an ambulance is a type of vehicle. So let's explore that one a bit more now. So we said, what is this? And somebody shouted out a vehicle, but somebody also shouted out, shouted out as an ambulance. Somebody also shouted out that this was a vehicle, and that's also correct. So in object-oriented programming, we can have classes that are themselves based on other classes. And that's a concept known as inheritance. Okay, so what we could say is, yes, we could create a class called ambulance, but maybe we might want to, in our code, have lots of different types of vehicle, in which case it might be worth creating a class called vehicle and then have these different types of vehicle as their own separate classes that inherit from the class vehicle. Okay, so we could create a vehicle class that has attributes and methods that apply to all types of vehicles, so we don't have to keep rewriting that. And then we can create, as an example, an ambulance class that says, okay, all vehicles have a registration number, all vehicles can drive, all vehicles can park. Okay, so we don't need to, when I create my ambulance class now, I don't need to specify all that again. I can say that this inherits from the vehicle class. So everything is carried across. So I don't need to specify the fact that we need a registration number, that's already in vehicle. I can just specify the things that are unique to an ambulance. So, ambulance is a type of vehicle that also has, whether a patient is on board and whether the siren's on. And similarly, in terms of methods, yes, it can drive and park like any vehicle, but it can also load and unload patients and turn on and off the siren. Okay, and those things won't apply to all types of vehicle. And this process is known as inheritance. And in inheritance, we talk about a parent and a child. So the child inherits the methods and attributes of the parent. So here the vehicle class would be the parent class, and the ambulance would be the child class. So you can say this is a vehicle. We want to create a class that is basically a type of vehicle that is like vehicle, but with a few little added bells and whistles. So we define ambulance as being a child of the parent vehicle. Okay. You'll see when we come in to do this in Python code that actually this saves you a lot of time, because it means, let's say you had a piece of code, a computer program, and you were writing 10 different types of vehicle. There'll probably be lots of stuff that is common to all of those things. You don't have to write it out in every class definition, all the same things. Driving may be the same in every case, parking may be the same in every case. So you don't want to have to do that all the time and keep repeating yourself. And this is what object-oriented programming is all about. You try and repeat yourself as little as possible. So instead, we can say, well, this is stuff that's common to all vehicles. So now I can just say what's unique to an ambulance, and just say I'll inherit from vehicle. I am the child of vehicle. Okay, makes things a lot more efficient. And of course, that allows us to then do things like this. We can say, well, from vehicle, not only can I create an ambulance class that inherits from vehicle, I could create a bus class, which is a bus is like is a type of vehicle, does all these things, except it also has a passenger capacity, and you open and close the doors and take the fare. And similarly, the car, well, a car is a type of vehicle, it has all this kind of stuff, but unique to a car is, well, we might want to store the number of doors and opening and closing the boot, etc. So again, it stops us having to rewrite stuff that's going to be common across all of these things. Now, it's also really important, this kind of goes back to what I was saying a little bit earlier, there are no right or wrong answers that say how you should break up your code into classes. Okay. Sometimes it may be, depending on what you're trying to do, it might be sort of glaringly obvious how you would structure it. Other times there may be multiple different ways, or it may be not obvious at all, and you may need to think sort of creatively. General rule of thumb is whenever you're thinking about stuff like this, think about whether there are self-contained things within your system that have stuff or information and do stuff. And try and think about your system as being a collection of things that have stuff and do stuff, and sort of put all your all your variables and all your methods associated with one of those things. Okay. And again, just to point out, as I did right at the start, object-oriented programming is difficult. Okay, it is not intuitive, and it is, even if you're an experienced coder, it can be tricky to get your head around it. So don't press yourself too much to try and understand this right from the off. It is a slightly more unusual way of thinking about things, but is incredibly important and really, really will transform the way in which you code. But as I say, you're going to get lots and lots of practice when throughout the course. In fact, this morning I talked about one of our sessions will be on agent-based simulation. If you remember back, I said that agent-based simulations where you have individual agents and each of those sort of have their own behaviors and they interact with each other. Agent-based simulation is a really nice demonstration of object-oriented programming, because effectively you have each type of agent is a class. And you say, well, that each agent has information they carry around with them and things that they can do, their behaviors. And that's basically what object-oriented programming is. Imagine a patient who is entering your emergency department or your doctor's surgery or wherever it may be. Imagine them carrying pieces of information. Think about them sort of carrying almost a clipboard of stuff like their name and their age and all that kind of information about them. And some of that stuff might update over time. Some of it will remain constant. And there are things that the patient might do, like they might attend something, or they might leave, or they might do other things, okay? And those are the methods. So things that it has, pieces of information that it has, and about it, and things that it does. Okay, so you probably saw this coming. What I'm going to get you to do now, go back into your groups, and I'm going to get you to go back to your designs for your cash grab shower system. And I want you to imagine that you've been asked now to make sure that your cash grab shower system is object oriented. Okay, so I'm going to get you to basically again draw up some diagrams that will show what classes you think you would use. And again, no right or wrong answers. Just think about how you might break that down. The classes you think you might use, along with what attributes and what methods. And for each of these things, for the attributes and each of the methods, I want you to write a little short description of what each attribute stores and what each method is doing. So an example here from the vehicle example, I've set up my attribute. Here are my attributes. Here are my methods. And this attribute here, registration number, well, that's a string variable that stores the registration number of the vehicle. Drive, that's a method that causes the vehicle to begin driving at a given speed, etc. Okay, so it's really just to get you thinking about how you might break up something like this into an object-oriented structure. But there are no right or wrong answers on this. So just think creatively, and it'd be interesting to see what you come up with. So what we'll do, I'll ask a couple of groups to share at the end. So we'll go till 20 past. If you want to take a few minute break somewhere in there, please do. But otherwise, we'll come back at 20 past and I'll ask a couple of groups to share. So that should give you about half an hour. Okay. Any questions about any of that? No? Good. Okay. Excellent. I will stop sharing and I'll open up the breakout rooms. Hi everyone. Okay, welcome back. Really good to see again some really interesting discussions about how you'd frame this in an object-oriented way. and yeah, I see some people really sort of embracing it, others a little bit more confused. That's fine, as they don't. It's all a bit weird at the moment because we're teaching coding principles. You haven't really seen the code yet. This will gradually make more sense, but already I'm starting to see, the kind of right kind of questions, the right kind of logic that you're starting to ask. How you would break down your code into sort of chunks and say, well, that chunk kind of belongs to the user, and the user can do these things and has these attributes. That's the kind of logic you need for object-oriented programming. So yeah, just bear with it. It's all going to seem a bit weird and abstract at the moment. Now, hopefully, when we get onto the Python itself, this will start to make a bit more sense, and you'll gradually sort of chip away at it. But you will get lots and lots of examples of object-oriented programming throughout the next 6 months. So what I'll do, we'll get a few groups to show us the different things they came up with. So let me share my screen, and we will spin the wheel once more. Where are we? Over here. Let's spin the wheel and see who's next up. Paula, you're up next. Paula, want to share this?
Sorry, it's on mute. I'll bring that up now. Oh, hopefully you can see that. So we've identified kind of two main classes, which are the shower and the person. We've then also added in an additional class for language settings of the shower, because we want Chalk Industries to be worldwide and accessible to all. So in the shower, we've kind of identified the attributes for the ID and name of that shower. Then we've also got settings for the min and max temperature, as well as the current temperature that it's at. Language, which would then kind of pull from the language settings. Time of day, so that'll be used when it checks for morning or afternoon. A volume setting, so people don't get deafened when they step into that shower. Current timer length, so that'll be used for when we're looping through the 5-second timers, etc. And then whether the shower is occupied or not is a Boolean. And then the bits in bold are the methods, so increase in the temperature, decrease the temperature, turn the shower on and off. A function for the audio announcements, so for stating the person's name, etc. And then the timer function. For the person, so we've got user ID, name, and age. The age we've added in, as we thought, kids might not want a hot temperature, so you'd want to kind of link that in so you can set a max for the child. So you've got the perfect temperature that they would set, a custom field for max and min temperature, and then a history of previous shower temperatures. And then the methods, we've got enter or exit the shower, begin the shower, the audio input, so if they say too warm or too cold, and then a function for the announcing their name, so the shower can pick that up. And then for the language table, we just got a couple in there, the language itself, the ID, and some phrases that are stored in there as well. And that's us.
Brilliant, thank you. No, again, really creative the way you've thought about that and thought about things that might relate to the different objects there. So yeah, really good, excellent, thank you. Okay, so let's spin the wheel again. We've got time for another one. Let's spin the wheel. See who it lands on now. It's Zylog keep getting away with this, but it's Antic. Okay, Antic. Somebody, I think you want to share your screen.
Yeah, hi, that was me. Sorry, let me just. Okay, hopefully you can see that. So we just counted the shower as the class, and then had the temperature and all of its different settings as being an attribute, perfect temperature that you can store, and the user profile that gets stored, and the time, and then the sensor that recognizes people as being in the shower. So those is what we had as the attributes. And then for the methods, we've got increase of the temperature, decrease of the temperature, turning the shower on or off, the talking, then a water flow or pressure, and something that gives it the ability to store the data variables. Then we counted the person as being a separate class, but we haven't kind of listed the attributes and methods for those.
Okay, no worries. Thank you. Well, again, nice, interesting way in which you've approached that again, and something pops up whenever you're thinking in an object-oriented kind of way, that very often you'll kind of start off with one or two classes, and then as you go through, you might then start to find that actually that might make more sense as its own class, particularly if you're thinking about actually that thing that I've written here, that could be really useful when I design my smart lamp or whatever it may be. So maybe I should separate that out and have that as its own class. So that's a kind of iterative process. So yeah, really good. Thank you very much. So I think we've got time for one more, but I'm not going to spin the wheel because I don't know about you, but I certainly felt Zilog got away with it twice today. So I'm going to pick on Zilog because it's my prerogative to do so. So does somebody from Zilog want to present? Afraid you don't get away with things here.
Well, shall I do this one? I'll go on. I think mainly to show you just the wonderful extensions that we managed to come up with more than the actual class diagrams.
That was the other reason, because I did drop into your group and was very impressed with those.
Oh, incredible! Some of the ideas. We've got Alexa integration. We've got some non-verbal cues so you can control with gesture commands. We've got some usage stats for long-term longitudinal analysis. I thought there was a brilliant one about reducing the shower temperature to keep people green, to get people out of the shower. Fantastic stuff. So, but on the class perspective, I think we've got a very similar approach. I think we've probably added an element, a class that wasn't seen before, which is the shower system idea. So the one that kind of creates both the kind of shower instance and the user instance, and just helps coordinate everything together. And yeah, it's primarily there just to, as I say, create those objects and run the shower. We can also add new users into the kind of database. The shower's got the kind of three methods that we talked about in our current process with this sort of subroutines here. So we've got the ability to heat, cool, and set the perfect temperature, along with the ones that mentioned earlier in terms of start and stop. The person one I think was quite interesting, really just looking at how far we go into defining the person, or whether we, do we need to create a whole object for them, or do we see them as a user of the system? So whether we need to put in all the methods for speaking and interaction from a person perspective, we weren't quite sure how deep to go into that. So yeah, your steer on that that'd be good. But yeah, mainly I think we were very happy with our shower extension projects. So future of showers was provided by Zilog. I think will be
excellent. Oh, clearly, yes. with a Zilog processor, I hope, running the heart of this. Brilliant, thank you. And yeah, interesting point you made there about whether, and it came up in a couple of groups actually. It can seem a bit weird having a class for something that physically exists in the real world, because you can end up thinking about, well, what am I talking about, the things that the user is physically doing as a human being? It can get a little bit blurry. I think the thing you always need to remember is that what you're doing is you're using this to structure your piece of software. So it is the things that are, if you weren't writing it in an object-oriented way, what methods and attributes, what methods or functions and variables would you have? And which of those feel like they belong more to the user, and which of those belong more to the shower or the voice control unit or whatever it may be. So that's a good way to sort of divide that up. It's not so much about the user as a human being. It's about the user as its representation within a software system controlling a shower, essentially. So it's a bit weird to get your head around. And as I say, the extra layer that you've got is that this is still very abstract at this point as well, because you haven't actually been working with any code. So hopefully, as you start to see the code, that will improve things as well. Just to also flag up, as I saw a question flash up about sort of answers, in terms of what Sammy and I would have done. So we haven't for this, although I think Sammy volunteered. Thank you, Sammy, to put together her own interpretation of what she'd have done. Again, there's no right or wrong answer. Just to say, a lot of the exercises as we go through, there will be solutions that we post-op, which are the way we've approached something in terms of a piece of code or whatever it may be, that we would then upload. We'd normally upload those after the session, because we don't want you getting distracted by that before, but that would be made available to you if you want to look at that. And that's particularly useful if you want to just compare the way you've approached it versus the way we have, or if you just got completely lost and thought, I don't get this, I need to see how I would have approached this problem, then we'll have that. So we don't have anything official for this one, although thank you, Sammy, for volunteering for that. But many of the exercises as we run through, we will have solutions, as it were, or proposed ways in which this could be approached. But there will be very few exercises where there is a single right answer. So don't worry too much about that. Okay, so we'll close off there. We've only overrun by 2 minutes. That's an improvement over last week. We're getting better. So thank you all for today. Hopefully you've enjoyed it. We've covered both conceptual modelling this morning and kind of principles of programming this afternoon. And I can feel in the air that you're all eager, raring to go to get hands-on with some Python and let's get technical. So next week, that's exactly what we're going to be doing. And we're going to be exploring the tools that you're going to be using, primarily VS Code, and explaining how you're going to be using VS Code both for standard Python files and also something called Jupyter Notebooks. We're also going to be looking at Google Colab as well. So you will need your software installed, because from that point forward we will be using things. There will be certain things that we will set up with you. So next week will be a bit of a follow along. There'll be a lot of places where you are sort of following along as we go along. Now we fully expect that next week we will encounter issues. Some of you will say, that doesn't work, something's gone wrong. We've kind of deliberately done this so that you find out about those little problems. And I think I know what the problem will most likely be, if you do have a problem, before you get into the coding itself. There will be backup options if your IT department is slow to resolve it as well, that will work for a while. So don't panic too much about that. If you run into issues next week during the session, it's part of the reason we do it a little bit separately. So don't worry too much about that. But you will be doing some coding in a slightly different way. We won't be teaching you the bits of code as such, but you'll be exploring bits of code and trying your first tentative steps in the world of Python coding. So next week, a bit of a different session, and we'll get used to VS Code and start your Python journeys, which for the next month is basically what you're going to be doing. Pretty solid. So fantastic. Thank you all, everyone today. Fantastic to hear all the discussions going on. Some really excellent work. So well done, everyone. And I look forward to seeing you all in a week's time. Thanks, everyone. Bye-bye.
Thanks, Dan.